So, yeah. Yeah, so the live stream is on. I guess we'll wait until it's time and then we can start.
Chris, are we stuck?
Think. So what's your experience, Christian?
Yeah, I think we can start.
Okay, so welcome everyone. Welcome to the industry session of this QCrypt 2020. So as always in the industry session, we try to have a kind of feedback between all the communities to the more applied topics and industry. So, so this should go both ways, as always. So I might introduce myself. So I'm Christoph Marquardt from the Max Planck Institute for the Science of Light, and I'm chairing this session together with Akihisa Tomita. And when we designed this industry session from the steering committee, we thought it might be interesting that we give you some insight about what is happening in the world concerning two topics. Basically, one topic is standardization activities. So right now, quantum cryptography is so advanced that there is a lot of activities right now worldwide concerning standardization and even certification. And so there will be one session about that topic this morning. And another session will be about activities, worldwide activities about quantum networks, or QKD networks, where one really tries to investigate quantum cryptography in realistic networks. And so this will be part of the second session. And we are quite proud that we got some excellent speakers that will give us talks about these topics. And I will start right ahead. Now, I will say we have those talks, and about 10 minutes talks that will update about those different topics. And then there will be time for about 5 minutes questions. I will try to coordinate a little bit the questions. As always, there will be more questions probably. Then there's always time to ask the speakers afterwards in the breakout sessions in the meeting greet rooms. And in after those talks, there will still be a little bit time to for discussing a bit more general topics, because I think it's nice to have all those excellent experts around, and that's a very good opportunity to ask questions towards those topics. Okay, so with that, I want to start the first part about the standardization activities. And so the first speaker is Hao Jin from the QAS Quantum Network, and he will be telling us something about the activities for standardization in the ITU and ISO groups. So welcome very much to Hao Jin.
Okay, thank you. Can you hear me?
Yes.
Okay, thank you. Thank you for the introduction. So I will share my slides. So can you see the slides?
Yes, we see your PowerPoint.
Yeah. Okay. So can I start?
Yes, please go.
Okay. Thank you. First of all, thanks for the organizer to introduce me, to invite me to bring this talk on standardization of quantum cryptography in ITUT and ISO. I think this is an important progress that recently has been conducted. My name is Hao Jin, and I work for QAS Quantum Network as a senior researcher. Before joining the company, I was a postdoc in Waterloo and a PhD student in Telecom Paris, both on QKD. So I have the background in both academic and the industry. I'm also a contributor of several work items in ITU and ISO, and serve as a liaison officer. So today we are going to talk about the progress of QKD in ITU and ISO standardization progress. So as we know that QKD is a mutual technology that has been achieved many fruitful results since its invention. So we have commercial product, and we have QKD network implementation, and we also have QKD in space. In order to further expand the usage of QKD, one important topic is standardization. So in particularly, the international standardization is very important. So there are so far 3 important international organizations. So first one is the International Organization for Standardization. I guess this ISO, everybody heard about it, and it produces many standards in our life. The second one is the International Electrotechnical Commission. It deals with the standards mainly for the electro and electronic related technology. And third one is the International Telecommunication Union. So this is actually the first global international organization and also the first standard organization. It is a special agency of the United Nations for the information and communication technology. So recently we have conducted several QKD standardization activity in this SDO. The Martin from SC will introduce the work in SC in the next talk. So in this talk, we are mainly focused on ISO and ITU. So for the ISO, it's actually the ISO IEC Joint Technical Community on the Information Technology, which has one work item on the QKD implementation security. To be noticed that there's also activity on post-quantum cryptography and quantum computing in ISO. So another important progress is from ITU that in several groups there's conduct activity on the standardization regarding to the QKD network on the network aspect and the security aspect, as well as there's newly established focus group on the quantum information technology for networks, which actually a pre-standardization group to pre-study the standardization issue. So I will summarize all this activity in this picture. So this picture is actually the figure from one of the recommendation produced by ITU SG13, which is Y.3800. This is the first international standard for QKD network. So this is a QKD network based on trusted node. Actually, this is very similar from what previously academic proposed. It has several layers. The standardization activity conducted by ISO and ITU is first for the ISO, it's on the QKD module security test and the certification method. And on the network part, ITU SG13 conduct the study in the part of network, all this network aspect. And SG17 deals with all these security requirement related issue. So I also mentioned the pre-study works carried out by focus group from ITUT. It's also it addressed the issue in the different layers. For example, the user case for the application layer, the classic protocol in the control and management layer, and also the QKD protocol and transport technology in the quantum layer. So I will go one by one to introduce this progress. So first, we go to the ISO work item. So this ISO work item actually address one of the most important issue for QKD, which is the implementation security issue. So it's a high-level framework under the common criteria framework for the security evaluation of QKD module. So actually, if you have worked with information technology, common criteria, it's a very universal framework for the cryptography system and the security system. But there's this gap that in such framework, the QKD part is missing. So this work item is aims to build a baseline for this security work. So it will serve as a baseline for the further security function requirement for the protection profile and the security target when we look at the specific certification. So this work item has two parts. First part is the requirement. Second part is the text and evaluation method. So we consider the general model for the QKD transmitter and the receiver. So all these yellow box are the one we consider for the first part, analyze the threats and impose the related security function, and also for the part two, it's the security evaluation method to address those threats. So this is pretty much the ISO work that has been initiated from 2018 and now it's under development. So let's move to the network part. So this is only a work item from ISO. So let's move to the ITU part. So the first part of standardization is in the SG13. This group mainly deal with networks issues. So probably it's a good place to conduct QKD related standard development. So in the question 16, it's mainly deal with architecture, framework, and function requirement. This related technology on the QKD network. In the question 6, it's mainly deal with the quality of service on the network part. However, there are some recommendation or standards seems a bit advanced. For example, this one for machine learning based QoS for QKD network. I think this one is a bit advanced even for academic. Nevertheless, in this group, it has already published 2 recommendations on QKD network, and for other 3 on the key management and other layer has been consented very recently. So another group which study the QKD standardization is in SG17. So the topic of this group is on the security. So actually, quantum noise random number generator is also in the scope of the study area of this group. So actually, the first published international standards on the QRNG is from this group. Also, on the other than that, there's several security-related standards on the QKD network, including the overall requirement, key management, trusting node, and so on. So in this group, it's mainly deal with the security aspect. Then we go to the last group that I mentioned before, that it's for a focus group on quantum information technology for networks. So this is actually a preparation group for the standard. So it does not produce any standards, but it will do some pre-study and pre-standardization activity, which means it will do the gap analysis, do the technology status review, do the standardization analysis, and give some future suggestion. So the output of this kind of group, it's a technical report, which with no normative contents. And it's a good platform for academic, industry, governments to join. So it was established from last year, and we already hold 5 meetings, including 4 e-meetings. In this group, the working group 2 is on the QKD network topic. So in this part, we have several interesting topics, including the terminology and the use case. Also the QKD network protocol, including the quantum layer protocol and classical layer protocol, as well as the transport technology, and also another report on the standardization outlook. So who are the main participation from these activities, standardization activity? So actually we have quite a few of participants from all over the world, from Asia, from Europe, North America. So some of them are already in the field for a while, some of them are new. So people may ask how to participate into this activity. So there are several ways. So for the ISO, it's restricted to the experts for each country's national body. And for the ITUT, it's based on the membership base for the study groups. But for the focus group, it's an open platform that is free of charge for everyone. And it has newcomer friendly and flexibility for the newcomer to join the activity and to learn how to formalize the standards and to give suggestions for the future work. And it covers a wide range of topics. Also, there's possibility if you work in some other SDOs, the lesson channel is also a good way to notify or give comments to other work items in different SDOs. So in the end, so we have we want to summarize what has been done so far in this different group. So around the topic of QKD network. So as we can see, for the ISO, we have QKD module security, and for the ITUT, we have security and network aspect. For the focus group, we have other interesting topics related to protocol transport technology. Of course, there are some other topics not covered yet. So at this particular moment, it will be interesting to look at the coming 5 years. There could be more potential works in different SDOs to further develop the standards of QKD related technology. This is my talk. Thank you.
Thank you very much. Thank you very much, Hao Jin. for this very nice and informative talk. Now I think we have time to have some questions for this talk. So if you have some question right now, you can just type them into the question and answer box you see in the right left corner. Maybe I will start with one question. So there's also, when you look at security aspects, there's also a lot of national aspects you have to consider, right? And national certification rules and so on. So how do you try to make this kind of compatible with those rules, which might vary, right? Very much.
So for example, for the QKD module security evaluation, so actually it's under the common criteria framework. Actually, this is a method used by many countries. So what we want to do is to fit for the current system, to fit QKD inside, instead of create a new framework, particularly for QKD. So I think as long as the country consider the common criteria approach, so this kind of standard in the future will be somehow compatible with your country's evaluation and certification method. That's my feeling. Thank you.
Mm-hmm, mm-hmm. So is there any other question? Always have also time to think about it, and we can ask questions later on in the discussion. Then I would thank you very much, Hao Jin.
Thank you.
So there's a virtual applause now, which is of course complicated to do in the virtual session. Now the next speaker then is Martin Ward from Toshiba Research Lab, UK, and he's talking about the standardization activities from ETSI.
Hello, everyone. Thank you very much for the opportunity to talk today and describe what's going on in ETSI at the minute. So I'm currently the chair of the ISG there. The ISG has been working on QKD for a number of years now, focusing on three main areas. So our activities are on security, so both the practical solutions for secure implementations, and also focusing on now evaluation and certification aspects. Second area is metrology. So this is related to security in many ways, knowing how components and systems are behaving. These often require measurements at the single photon level, and there are a few existing standards available for some of those tests. And then thirdly, we have networks and interoperability. So integration into conventional network infrastructures and interfaces to promote adoption and interoperability and development. So initially, I'm going to talk about security. So QKD is a rather unique security proposition. It's quite different from things that have been certified before. So in terms of taking devices through the certification process, there are lots of new challenges, both for companies presenting devices, but also for the national bodies and certification labs to evaluate them. So it's very useful to have specifications that have been reviewed by a wide range of experts. That's going to help ease the sort of facilitate the certification process. So also certification security analysis systems needs to consider all aspects of security. So we need to put in experts from with a range of established security skills. In addition to those with QKD expertise. So the new kind of activity within the ISG on security is that we've started to write a protection profile for QKD systems. So This again has been written, as Hao-Chin was talking about, the common criteria frameworks. This is also one of the common criteria frameworks, so it has broad applicability. The work's being performed in collaboration with BSI Germany, and we're employing an experienced certification lab to help with writing, the technical writing, to make sure it's set out all correctly in terms of common criteria standards. So we're going to consider prepare and measure protocols only in the protection profile, and the target of evaluation that we're considering is that of a pair of QKD modules. So it's really a point-to-point, the basic sort of point-to-point security that we're considering. So we think that the protection profile is going to take around about a year to write. So we're expecting to finish that around summer 2021. But in addition to this, we'll also be working on a number of additional group specifications that can be used as background documents for people who choose to take to base security targets on the protection profile that we're producing. So a document that we published a while back was on security proofs. So really looking at a security framework for, a framework for statements of security on QKD implementations. And at the minute we're updating that, having another look at some of the things that have evolved and revising some of the definitions in it. So that's an ongoing task that's coming to conclusion around about the next month or so. I mentioned background document. So we have one document analysing implementation security of against Trojan horse attacks protection that you can have in one-way QKD systems. So in this document, where we're analysing giving design guidance and passive countermeasures against attacks. So this will be one of the documents that will be a potential background document for people to use if they're writing a security target. I would just highlight a white paper that actually produced a couple of years back, which gives a nice introduction to some of the challenges and solutions to implementation security issues. And then one other piece of work that we're looking at starting a new work item on at the minute is on the design of classical interfaces for QKD systems that include authentication. So obviously authentication is a key part of any QKD protocols, and it's also critical in terms of the interfaces that a QKD system is going to present. So we'll be looking at protocols used in discussion channels and auxiliary channels, management interfaces and key delivery interfaces. And authentication schemes such as Wegman-Carter for discussion channels and related systems, and also appropriate uses of public key algorithms in QKD systems. So the related area I mentioned was metrology of components and systems. The reliable characterization is critical both for security analysis, but it can also be useful to help to stimulate and develop the supply chain for components for QKD systems. It's important to understand and be able to specify what you want when you're building systems. So we're fortunate within the ISG to have a number of national metrology institutes involved in this work. So a few years back, we wrote a group specification on component characterization. So taking the measurements you need to do on individual components that are going to be systems are based on. So that's quite a detailed document, and again was driven by some of the NMIs within the ISG. At the moment, we're working on a document looking at the characterization of the optical output of QKD transmitter modules. So there are a number of additional challenges when you start to try to measure things within a complete QKD system. You've got interferometers and things sitting in front of your components, and you have to think about how you extract information about what signals are being sent. So that's a development document that's running at the minute, and we'll then probably this year, we'd expect then to move on to a document looking at QKD receiver modules. So in terms of networks and interoperability, so obviously an isolated QKD link can serve certain use cases, but many require you to develop larger networks. Within the ISG, we currently consider that it's too early to start looking at interoperability down at the quantum channel level, but systems still need to be able to talk to each other, and you can construct a QKD network with multiple vendors in the system, as long as they can then talk to each other. So we need external interfaces and links to management systems. So in terms of actual APIs, we have a couple of APIs for people to use to extract streams of keys. So first of all, a low-level function call-based application interface that we published back in 2010. That's just updated. That has just been approved and should publish in the next week or so. We also have a REST API over HTTPS that's been used by, it's implemented in a number of QKD systems and also a number of cryptographic applications like link encryptors. And it's very easy to use, low barrier to entry API for requesting keys from a QKD system. The other area that we're actively looking at is interfaces for use where you start to integrate QKD into SDN. So software-defined networking is becoming important in many areas. And we have one document that is coming to a conclusion, looking at the control interface, so the interface between the SDN controller and an SDN-enabled QKD module. And we're just starting another work item to look at the kind of northbound interface of that. So an orchestration interface between the QKD controller and the SDN orchestrators, looking at a number of distant aspects. And both those documents will look at the workflows and resources and performance and reporting and so on that's necessary. And that one is just starting, as I said, and it's due to finish in September 2021. We have also a look at more generally at network architectures that can be used in QKD. So we're writing a group report on this, analysing some of the experience that ETSI members have, looking at a range of different schemes and components within those, and how components need to talk to each other within a network. Okay, so the ISG is an international, ETSI is an international member-led SDO. Its documents are available to download for free. And it has a range of experts across manufacturers, system vendors, operators, academics, and NMIs. And we have active members from many different countries around the world, so it's not limited to Europe. And membership of the ISG is open to anyone, and it is possible to participate whether you're an ETSI member or not. Yep, people are very more than welcome to look at the website or to contact me if you're interested in more information. Thank you.
Thank you very much, Martin. Also here the talk is now open for questions. If you have some questions, you can type them in the question and answers, or you can think about some questions for the discussion round later on. Maybe one question from my side, and that's maybe a big question. So we heard now the talks from ISO, ITU, and ETSI, and there are, of course, some, I would say, interfaces, right, where you can interface the different standardizations. So how is made sure that these kind of interfaces work out well?
So yes, obviously so both the ISO document and the protection profile that we're working on are written under common criteria. So we hope that those can interface quite well, and that you can you certainly be able to use the ISO document as a minimum, as a background document if you adopted the protection profile. It's a challenge to try to harmonize, but we have people who are active in both groups, and we're looking to try to ensure that you can use the documents as much as possible together. I think it is. There are lots of challenges in terms of thinking about terminology, for example, making sure that if you use the terms in the same way across the SDOs, it's going to make it much easier for us to use these documents in combination and to reference each other's documents. So I think I didn't mention it, but one of the things we're working on is a bit more of a review of terminology and updating our vocabulary document and trying to ensure consistency within ETSI documents, but also talking to the other SDOs to try to ensure that we use certain terms that are critical in a uniform way. And also for QKD experts, we have to think about not only using terms in a way that we understand within the QKD community, but also to make sure that we use them in ways that are consistent with the ways that they're used in existing security fields at the minute. So I think that's an important challenge in terms of making these documents work practically together.
Okay. If there's no more questions so far, then thank you very much for this very nice, interesting talk. And then we will proceed to our next part, and that's kind of an update about projects worldwide. So about testing quantum cryptography in networks. And so I'm happy to introduce the first speaker, that's Cheng Shipeng from USTC, and he will tell us about some activities in China right now. Please. I think we can't hear something. So maybe your microphone, you can check, you can double check. So we can see your screen, your shared screen, but we can't hear you. At least I can't hear you. Christian, is that the same for you about the audio?
He is unmuted, but we cannot hear him.
Yeah, so maybe we have another speaker first.
Yeah, maybe we can. So Cheng Shipeng, we see your slides and you're unmuted, but maybe if you speak something, because I thought I did see some signal on the virtual microphone, but
we also had video before.
Yes,
we don't have that anymore.
Some signal, but so maybe we do first another talk, and then maybe you can just log in again. As always in computer systems, restart. And something doesn't work. It's a universal.
This is the same I did before. So Christoph, maybe I could start.
Yes, that would be perfect. So then let me introduce Andreas Poppe from the Austrian Institute of Technology, AIT, and he will then be talking about what is happening in Europe with the Open QKD initiative. And then later on, we will then hear about the Chinese activities.
So can you hear me and can you see my screen?
So the screen is still from Cheng Shipeng. Okay, now it goes. Yes.
Okay.
Yes.
Okay. Yes. So also the system tried hard to kick me out. Hopefully, I can restore it well. Yes, my name is Andreas Poppe. I'm with the AIT again, and we are the leader of this big EU QKD testbed project with the name Open QKD. So, but let's first go a little bit back in history. So between 2000 to 2010 or so, the community could successfully demonstrate a series of QKD network demonstrations, which really led to some nice, highly cited papers. But at the same time, these QKD demonstrations totally failed really to open a market and attract some users from the security community, and also tells the telecom community that QKD maybe needs some different ways to transmit the signals. The EU waited another 5 to 6 years or so, but luckily they changed somehow the mind and restructured the funding possibilities for quantum technology completely. In the center, we have this QT flagship projects, and we have different pillars. I'm sure you know this picture. And one of the projects out of the communication pillar, which is anyhow most suitable to talk about, is CIVIC. Just allow me one single slide, because at this time, starting in 2018, we already included 3 telecom providers in this flagship project. They are Telefonica, Orange, and Deutsche Telekom, in order to think about how to transmit the signals in the network. And together with them, and this was a work together with Deutsche Telekom, we made a kind of reference network and tried to find out how to distribute the QKD systems that the telecoms by themselves can use the keys to secure management plane, control plane, and the data plane. But this is, of course, was too less, and very luckily, there was the next step. It was this project, which is here called an Open QKD. It's a QKD testbed project, which has not the goal to have one single testbed somewhere, like you know from China. Maybe you hear the talk later on, but we want this would not match to the European structure. In Europe, we have many different groups around, equally spread nearly, and so the idea was really to build up even now 16 different sites where we have deployed fibers and want to put the QKD systems there, and not only go to the telecom use case we already have in CIVIC, but also find out what is the demand of the security community in order to really use QKD systems at the end. When you put all the logos from the 39 partners across Europe, it's really right impressive, but it's also a big and a little bit complicated project, of course, then, but the main aims are, of course, to raise awareness for QKD. We want to make clear the community and the users that they should also consider QKD for high-end applications. And of course, EU is processing more and more to this EU big quantum communication infrastructure project. So we have telcos, we have QKD developers, suppliers, end users, academic groups. So this is really a nice mixture. And when you look to this European map, you can see the different test beds which are distributed nearly equally around Europe. We have some larger ones, some smaller ones, but the aim is really to be close to the different developers, close to the users, and not that some users or use case need to travel across Europe. We want really also to extract attention to newspapers in order to give really a big shot that QKD is spread out as much as possible. what is the state of deployment and the production? So up to now, we have really 25 QKD links already produced, but they're not spread out of for Europe because, of course, the Corona crisis hit us really hard. So we are behind 3 to 6 months, but we need to try to catch up. We also have some encryption devices, and we work on the second generation QKD systems and the key management, which was also somehow connected to the talks you heard before with the standardization. We have already one test bed running in the field. This was Geneva. This was easy in that sense because ID Quantique is the main QKD supplier, is really around the corner, and there are some small telecom operators there, and they really use QKD system now for their use case, also for instance for data centers. We have some upcoming use cases, Graz, Madrid, and Berlin. I just only want to briefly show one slide about Graz. So it's not fully clear, but here we have 4 links. It means each link consists for 4 dark fibers, and we populate the QKD systems and the telecom systems in there in order to do some secret sharing. We have high volume pictures from really patients, but we cannot use them, unfortunately. We distribute them to different cloud storages, and the user need to get the data then from the storages again. So this is my last slide. I just want to point to our newsletter. We really need to start it now. We'll also lag a little bit behind on that. We have a quantum industry board where we still search for participants. And what we also finished now was the first round of open calls. And we have a second round, and we have still some money left to distribute it to the main EU researchers, and so please stay connected with us that we can inform you about all things which are going on. Thank you.
Thank you very much, Andreas. So very interesting. So this talk is also open for questions. So while Chengshi tries to reconnect, I think, as you said, Andreas, there's some problems sometimes with the connections, right? So we can, but let's see.
Yes.
So maybe I can ask one question. So right now we see that there are some activities, all international, going on. Is there some ideas to also potentially look for use cases connecting intercontinental links, the different test beds, so to say?
Yes. So yes, we also have some satellites, research organization, not really providers, but as you know, this is then for the next step, this QCI project, which has not only a ground space, but also space-based links there to connect different metropolitan areas, connect different users together and so on. And this is anyhow the good question. And for me, it's still open to run if, for instance, a large metropolitan area, even in Europe, like Berlin and Madrid or Paris or so, will be connected first over satellite, over direct trusted repeater link, or already over the quantum memory-based real quantum repeater. So this is a really exciting time now.
Mm-hmm. So there's one question from Vadim Makharov. So he says, seems there are small networks only. Will there be a larger EU network, a backbone?
Not yet, not within OpenQKD, because OpenQKD don't have enough money really to deploy a lot of systems. We first go to the users and to the metropolitan areas in order to connect them first, and then try to connect the different metropolitan areas together, as I mentioned before.
Mm-hmm. Okay, thank you very much. So if there's no further questions, we still can have questions afterwards for discussion time. So how about Cheng-Shi?
Hello.
Okay.
Now is okay.
Okay. Very good, very good. So apologies for the technical troubles, but yeah, that's the usual thing. So very nice. So now we come to the talk by Cheng-Shi Peng from USDC, and he will update us about the activities in China. Please.
Thank you. Good afternoon. I'm sorry about the computer, my computer. I am Chen Zhipeng, coming from University of Science and Technology of China and CAS, and also come from the Quantum C-Tech company. Here I will mainly introduce our recently work to about the practical space ground integrated quantum communication network. As we all know, MORS satellite has been successfully launched for nearly 4 years. With this satellite, we have implemented a series of satellite ground experiment works. On the other hand, we have already built the longest QKD fiber network in the world. It is from Beijing to Shanghai, with total length about more than 2,000 kilometers. The Beijing terminal is already connected to our Xinlong ground station for MORS satellite. The combination of Beijing-Shanghai fiber quantum network and MORS satellite let us have a chance to show the feasibility of the ground quantum network. However, there are still many difficulties and technical challenges to be pushed in the future of realize the real practical quantum communication network. For example, our MORS satellite is a low Earth orbit satellite. It moves fast, which makes the experiment duration only about 6 minutes per orbit, and it has to work in the night. Therefore, in order to realize the truly global quantum network, we need to make efforts in many aspects, such as quantum stellation with LEO nano satellite, or the high orbit quantum satellite, and upgrade the present quantum network. The first thing we have to do is to develop the quantum stellation with low orbit nano satellite and low cost compact QKD payloads. Recently, we will carry a compact QKD payload with about 30 kilogram on the standard satellite. Meanwhile, we are also promoting to our own quantum nano satellite project. It will launch 3 or 5 satellites in 5 years, will service more than 100 users. Also, here is a big progress. We will design the low cost ground station for quantum stellation, because we know the ground of a lot of user. We expect a lot of use our satellite. We will make the ground station. We will make the ground station smaller, lighter, and cheaper. In a word, the ground station will be easy to place, install, and use. With this compact ground station, we have totally completed many times satellite to ground QKD and different cities, such as Shanghai, Jinan, Weihai. Here is a short video of rapid deployment in Jinan and in 1 day, performing the satellite-based QKD with the compact ground station. In order to overcome the problem of short time duration and small coverage range, the second thing we will plan to do is the high orbit quantum satellite. It will focus on the all-time or all-day quantum communication. Using the MEO or GEO satellite, the communication time during one transmit will be increased from minutes to hours. Furthermore, if we can break through the Earth shadow limit, we will be able to provide 24-hour service of key generation for some specific areas. For the payload, in order to overcome the higher China loss caused by the increase of orbital height, we needed to develop a higher brightness spaceborne quantum light source, like include the decoy stage source and the entangled phantom source. For the GEO satellite, the big optical telescope on the ground also should be upgraded. In order to reduce the background noise greatly, we have to use a single mode fiber to receive the photons to reduce the field of the view of the receiver. So, due to the atmospheric turbulence, the coupling efficiency of single mode fiber will be very low. To overcome this problem, we should develop the adaptive optics to achieve enough coupling efficiency. On the other hand, the present fiber-based network in China also needed to be upgraded. The goal of the upgraded backbone network will be safer, faster, and wider area. A new protocol, such as MDI QKD and TF QKD, can be developed to offer better security and great transmission distance. Recently, my college achieved the entanglement of 2 quantum memories via fibers over 10 kilometers, which enable the repeater-based quantum communication, paving the way towards building a large-scale quantum networks over long distance. For more detail of this new progress, you can find the corresponding talks of my college. Moreover, several new quantum backbone are planning to build a nationwide fiber network to connect most of provinces in China. Beyond that, we can also try to perform China integration between QKD and the classical communication. For instance, we have realized the China integration between a commercial QKD system and a commercial WDM system over 110 kilometers, together with China Telecom, Fiber Home, and so on. For Chinese QKD industries, under the support of the CAS and USTC, we founded 2 companies. One is the CAS Quantum Network, The company is focused on quantum network construction and operation, and promoting the wide application of quantum-safe technologies. Dr. Qin Hao has just given a talk on the QKD standard on behalf of CAS Quantum Network. The other is the Quantum C Tech. It is a Chinese pioneer and leader in commercial quantum information technology. Now maybe the biggest manufacturer and provider of quantum information technology product and service. Up to now, we have a lot of users in our fiber network, including one of the biggest bank of the world, ICBC, for data disaster protecting, and one of the biggest internet companies in the world, Alibaba, for data security. We have completed the chain of QKD industrial standard application in China. Finally, in a summary for the future large-scale quantum communication in low orbit, we need to develop cheap nano satellites to cover the Earth, to construct cheap and ground station. We also plan to develop high Earth orbit satellites to provide 24-hour service. We expect the lower cost of the global satellite and fiber-based QKD, perhaps less than 1 cent per kilobits all over the world. When we lower the cost of the price, a lot of security applications such as authority, bank accounts, online meeting, and other information security requirements will prefer to use QKD. If you can make the global quantum communication much cheaper, much safer, and much convenient to use, we can make it be the best choice for the future information security. This is our homepage and QR code. Welcome everyone to contact us. Thank you.
Yeah, thank you very much. Thank you very much, Chengxia. So very nice talk. So we are open for questions. So you can type it in the question and answers as always. Maybe I start with one question. For the satellite project, if you want to go for a geo satellite, so how big would you expect the apertures from the telescope to be so that you can deliver a key?
On the satellite, the telescope maybe 1 point, or maybe not. Will be about 0.5 meter or bigger, such as this. It is a general telescope technology on the satellite. We know now the biggest satellite telescope is about 10 or more meters. So 0.5 meter is not a very hard thing.
Okay. And maybe another questions before I see other questions popping up. So can you imagine also a kind of international roaming, connecting the Chinese network to other networks via some means, some channels?
I think our QKD technology is another choice, is different choice with the like a RSA, like a mass mode, or you a key transmission mode. So it will get if we and QKD method can to can use with can similar combined with the communication, like fiber communication. So the Chinese QKD network, like the fiber communication, will connect to the all of the world. It is I believe the QKD technology will combine with at least communication and with one device can provide the key transmission and communication. This is a basis is maybe a communication base of the internet.
Okay, thank you very much. So if there's no further question right now, then thank you very much for your nice talk.
Thank you.
And so then we come to our next talk, and the next talk is by Yoshimichi Tanizawa from Toshiba, and he will tell us something about the activities initialized in Japan. Please.
Oh, thank you for the introduction, and thank you for this opportunity. So in my presentation, I would like to explain the Japanese two national projects. One is a SIP project we have now conducting, and another project is global quantum network technology we have started now. So this slide shows the SIP project we have started from 2018, and it has 3 topics, and our team is focusing on the photonic quantum communication, and commissioned by the Cabinet Office Japan. And this slide shows overall layering architecture of the research target. The bottom layer is a quantum layer, so the QKD unit is located here and exchanging key. And the intermediate layer corresponding key management layer and the quantum QKD network control and management layer. In this layer, the key management agent manages keys from the quantum layer, and trusted node is located here and consists of key management agent and several QKD units. And the key management agent exchange key management information between other key management agent on the different trusted node via authenticated line. And the upper layer is application service layer. The key is provided from the key management agent to the application here. In our research target, we assume special types of application, secret sharing. Secret sharing is a technology for distributing data amongst a group of participant application here, and each of whom is allocated a share of the data, a part of the data. And the data can be reconstructed only when a sufficient number of shares are combined together. And the individual shares are of no use on their own. So in this project, we are trying to develop, integrate quantum cryptography technology as information theoretical secure communication and secret sharing technology, information theoretical storing technology, to develop, we call this technology as a quantum secure cloud. So this map shows 4 trials we are conducting. And in my presentation, we focus on these 2 trials. One is a biometric authentication data field trial, and another is a genome data field trial. So this slide shows a biometric authentication data field trial, and it focuses on the face authentication system, a user-friendly personal authentication method. And the figure shows an image of the face authentication system and the example of the system screen. In the face authentication system, reference face data is needed to be stored, and reference data should be referred. And this reference data should be protected, protection element under law. And apparently the biometric data cannot be changed even the data are stolen. So the face authentication system should be protected by quantum secure cloud technology. This figure shows overview of the face authentication system. In installation site, cameras are monitoring someone entering, who are entering. And when detect someone is entering, the camera and the processing servers send detected data to authentication server and referring database containing reference data and identify who is he, who is he. So this figure shows overall architecture of the trial system. With this system, the biometric system with quantum secure cloud technology protects the real data. Real data means Japanese national sports team data. I would like to explain this number 1, 2, 3, 4, 5 in this figure. So in the step one, the access control area, the camera detects someone is entering here, and the detected data is transferred from the camera via system control server to the data server. And this communication is secured with the QKD technology with one-time pad. And here at the data server, the database reference data are stored in a distributed manner using secret sharing technology. And when identify the user accessing here and allowed by the system, the user can access to the stored data here, the medical record data. And medical record data also stored in a distributed manner using secret sharing technology. And in step 4, this system also allows to access from the mobile PC to the data. In this case, the machine authentication and user authentication, including face authentication, should be performed on the mobile PC. And the data between the system control server and the mobile PC is secured by pre-shared key, not QKD, but this technology allows to access from the mobile PC. So next, I would like to explain another trial about the genome data research and medical domain. As we know, the genome data is very important for the genome medical and genome researches. And also, at the same time, genome data is very sensitive for the personal, for each personal. So in this situation, we have developed genome data transfer system using QKD technology and one-time pad technology. This research activity is a collaboration research of Toshiba, Tohoku University Tomo, and Tohoku University Hospital. And there are two sites, Toshiba's site and Tohoku University site. So the use case is as follows. The genome itself is delivered from the Tohoku University to the Toshiba's site. In Toshiba's site, the next generation sequencer is sequencing genome itself and generating the genome analysis data. At the same time, the QKD system transfers the genome analysis data to the Tohoku University as a result of the genome analysis. And the genome data is very huge. So we have 4 trials here, and we use different kind of genome sequence method. Trial 1 and 2 use a whole genome sequence, and it's in this case, genome analysis data correspond to the more than 500 gigabyte. And trial 3 and 4, we use a whole exome sequences. In this case, the genome data correspond to be 18 or 19 gigabyte data. To support this huge data transfer, we use our high-speed QKD system. The average security rate was 7 or 9 megabit per second here, like this. And this was a case trial where the actual first case where the actual genome analysis data transferred using a QKD technology with one-time pad. And please visit our team's poster, ID 117. This poster describes more detail about this trial. And another trial related to the genome data research and medical area is TB conference system for clinical use. So medical experts, including doctors, need this kind of TB conference system for discussion and genome data reference of patient cases. So in this trial, there are two sites, both at the Tohoku University, Tomo, and hospital. Between these two sites, the existing TB conference system is connected to the key management servers, and the conference data, including movie and reference data, exchanged between the TB conference system by key management server. And the key management server performs a one-time path encryption using a QKD key. With the result, the average key consumption of this conference system corresponds to the 1.05 megabit per second. Since our high-speed QKD system, secure QRate, is 10 megabit per second at the maximum, we found that our QKD system can support this TB conference system. And this was a trial where the medical expert, including doctor, joined and confirmed the validity of the TB conference supported with QKD system. Okay, and there is another poster explaining this trial. ID is 141. Please visit the poster. So this is our last slide, and we have started a new joint R&D project. The topic is Global Quantum Cryptography Network, and there are 4 targets. Target 1 focus on the QKD link technology for higher speed and longer distance, and target 2 focus on the trusted node technology, including system security to secure the node itself. And target 3 focus on the quantum relay technology to drastically expand the distance of the QKD link. And target 4 focusing on the network functions to support wide area and large scale network. We have started this R&D project as well as continuing SIP project for the several kind of field trial. Thank you very much.
So thank you very much for this very nice talk. So again, the talk is open for questions. So you can write questions in the question and answer box. So maybe I start with one question. So when you have those medical examples of using QKD links, so what would you say is the greatest challenge to bring that into kind of every hospital or every doctor's practice that could use it?
Okay, so so this case, the distance between these two sites is 7 kilometers, so relatively short. So that's why we could achieve this speed. So as usual, one of the recommended feature for the QKD to apply for the actual area is the speed of the QKD secure key rate. Yeah, and okay, and sorry, with these two field trial for the genome high volume data transfer and the TB conference system. So this is a very short and quick responses needed. So with these two field trial, we confirmed that QKD technologies can be supported to this kind of 2 different types of application. that was a good point, but I think.
Okay, so thanks. There's one question by Yong Shao. It reads, thanks for the nice talk. I'm wondering whether the encryption of the data using QKD and one-time pad or QKD and symmetric algorithm is used.
I'm sorry, I don't understand. Well, I don't understand
so
what.
Basically, the question is whether the encryption of the data that was used in these use cases was using QKD keys and one-time pad or QKD keys and symmetric encryption.
Okay, so in these all cases, we use a QKD key for the one-time pad technology. Yes.
For the one-time pad, so the data the data transmitted is using a one-time pad, not an AES symmetric encryptors.
Yeah, data is encrypted using one-time pad technology.
Okay. There is another question by Wolfgang Gerke. Is today a commercial QKD system from Toshiba available in Europe, as far as you know? So that's a very commercial question.
Yeah, we are not yet. Not yet, but yeah, we are investigating to start business very near future.
Yeah.
Thank
you very much.
Thank you.
Okay, so thank you also for this very nice talk. And so now we have the open discussion session. And so feel free. So we have now the opportunity, we have very good experts here that you can ask questions about all those topics. And as we learned, those topics are, of course, a little bit connected: standardization and networks and the deployment of all those technology. So maybe you can just type in your question in the question and answer box. Before, so maybe I start while you can think about questions. And what I always like when I have such experts here and around, I would say, okay, if you would have a wish, a quick wish, right? I mean, sometimes you can, there's someone who just gives you a wish, So what would you wish to accelerate the deployment of QKD systems? So maybe, I don't know, how Chin, we start with you.
Excuse me, you said it start with me?
Oh yeah, so the question is, so maybe all the panelists, so the question for everyone would be the same. If you would have a wish free, right? If someone would fulfill you a wish, what wish would you kind of have to accelerate the deployment of QKD?
Yeah, Christopher, so may I start? I know my wish already.
Yeah, sure.
Yeah, so I guess that everything is really a complex ecosystem, and when you take out one wish, it will not happen because the other things are still the problem. But I would really wish that photonic integration would work for QKD, enabled to have a cheap QKD system, which is also compatible to the QKD, to the telecom standard, REX and so on, that the different big vendors, Nokia, Ericsson, plus the Chinese ones, of course, can really integrate it in their systems and operate it.
So who would like to answer next?
Maybe I can give some comments. I have the same kind of feeling that QKD in the future should be part of the information technology infrastructure, like to be combined with the operator, telecommunication operator. So as today's RSA and AES, this kind of technology, in the future in certain critical infrastructure, the wish is that QKD can be real, like replace some of them and to be like really put in practical use and to to make its advantage to serve for our future network and other information infrastructure. Yeah, that's my wish.
May I?
Yeah, sure.
Yeah. So I think I hope many people from the various background would join the R&D and the business of the QKD area. So I think QKD area requires very broad technology, and very broad knowledge. So I hope for example, network technology and also the many types of IT technology researcher or engineer would be welcome to join this field. Thank you.
I don't know, maybe Martin?
So I think those points are right. So I think probably we can survive without integration between QKD systems at the link level, but the integration into the networks is what really is important. So yeah, compatibility with existing networks, integration with data. I think those are the most important points to get things integrated. And then I think, yeah, the sort of certification side to give people the assurance that the systems have been worked through properly and that they can have confidence in them. So.
Maybe Cheng Shou? Maybe there's some network problem. So I have, there's, okay. So Vadim Makharov posted, so he has a comment. I wish a whistleblower leaked that NSA has a quantum computer. That's, of course, it would be a boosting event. Yes, I agree.
My answer is general quantum compute, general quantum compute under the combination with commercial fiber laser communication network and make the chip design QKD technology. If we have this, we both have this, then QKD will be everywhere. Everybody and every country will need a QKD.
Okay, thanks a lot. So there's one question by Romain Leon. So Romain says, thanks for the nice talks. To build on the question from Yong Zhao, what is the view on the experts on this following controversial question mark statement? Combining QKD with AES, so the symmetric encryption, has limited cryptographic interest, right? So I think some people might claim that if you combine QKD with the information theoretical security with the symmetric AES, that it has limited cryptographic interest. So anybody want to comment on that?
I hope that the statement is wrong, but I'm not sure.
Okay, so basically it's really about the statement between the relation of this of the QKD and the security promises of QKD and symmetric, and the use with symmetric encryption. Right.
I mean, when you look to the telecoms, you need, of course, to transmit a high amount of data. And QKD can maybe now get to 10 megabit per second, but will probably not go to 100 gigabit per second within shorter time, but telecom would like to have it. And then AES is really needed because then it's interesting really to replace the keys in a short fraction, say every minute or every half an hour. And I think then combining QKD with AES has hopefully commercial interest for secure applications.
Further remark on that?
So I guess hopefully this leak from NSA is of a finite-sized quantum computer. So I think the use case where you can change the keys rapidly, you don't have that the future loss of once you've been attacked, you lose everything. So I think that's the, at least in the medium term where QKD has limited bandwidth, I think that's certainly where potential interest may be.
Okay. All right. So I don't see any further question right now in the question answer box. So thanks a lot to all the experts. Thanks a lot for your nice presentations and the updates. So I think it's always very refreshing and interesting what is happening worldwide. And it's good that we know what is happening worldwide. And if it is only to tell our governments that, there is something happening and we have to do something. So it was very interesting. And thanks for joining this session. And we will be looking forward to all the other talks at QCrypt. And please remember, you can also meet the speakers then in the meet and greet room and ask further questions and try to talk to them. Thanks a lot.
Thank you.
Thank you.
Thank you very much.
Okay, shall we get started? Perfect. Okay, so welcome back everyone for the tutorial session here at QCrypt. And I'm sure most of you are already familiar with the procedure. So before we start, just a brief word on how the tutorial session works. So feel free to ask questions on one of two ways. The one is in the question and answer Q&A feature directly here in Zoom. Or the other option is you can, during the talk, raise your hand and I can unmute you to ask your questions in person. And during the talk, there will be a few natural spots where we can go through some questions, or if I see that there's something urgent, I will briefly interrupt Masato and ask the question right at the spot. So if you have some clarification questions or anything like that. And yeah, I think now without delaying much further, I have the pleasure of introducing Masato Kwashi and his tutorial. And he will be speaking about security of quantum key distribution and in particular an approach from complementarity. So yeah, I think, Masato, if you're ready, you can start.
Yeah. Thank you very much for introduction. So I will start the tutorial about security of quantum key distribution. So I'm Masato Kowashi from University of Tokyo. So, this is the overview of quantum key distribution, and I'll send some weak light pulses to Bob, and Bob makes a measurement, and they accumulate the shifted key. Then they correct errors and also do the privacy implication to arrive at some final key here, and that they hope that this final key is secret from eavesdropper here. And aim of this tutorial is to explain how we can prove the security of QKD protocols against general attacks, focusing on the approach with kind of phase errors or phase error correction, which dates back to Meyers or Shor and Preskill. So I divided my tutorial to two parts. And the first part is about methodology of this method. So I will explain in 3 steps here. Then I will give you the application of this method to various protocols listed here. So, okay, let's start to the step 1. So the goal of the QKD is to create the final key, and the ideal property of the final key is summarized as these 3 properties. So there's no correlation to Eve, and distribution is uniform, and also there's no error between Alice and Bob. And it is convenient to describe Alice's key and Bob's key in Eve's quantum system in a single quantum state like this. So general state will look like this. So here, because Alice's key and Bob's key is classical objects, so we can describe by using some orthogonal basis here. Then Eve's quantum system may depend on key value in the general state. But the ideal state satisfying these conditions is look like this. So here, decoupled from Eve, and key value is also the same, always the same, and also the probability is the same. So this is the ideal state. So this is the goal of quantum key distribution. Now, it is convenient to divide this security condition to 2 conditions. So one is secrecy for Alice. So just care about Alice's key and forget about Bob's key. So we are talking about the state for which the Bob's key is traced out. So it's a property of state AE here, and the ideal state looks like this. So this is the secrecy condition, and the correctness is just this condition here. Now, if 2 conditions are met, then that means that the overall security is satisfied. Now, the starting point of the phasor approach is actually considering in what situation are we sure of achieving this ideal state between Alice's key and eavesdropper's quantum system. So obviously, if you prepare a qubit on the X basis eigenstate, then make a measurement on the Z basis here, then this bit would be truly random. Okay, so this is because this state is pure state. So pure state should have no correlation to other systems. So if you do this measurement, then you have a perfect 1 bit of key here. So you can easily generalize this to have k qubits in a prostate here, then make a Z basis measurement. Then surely you would have this ideal state here. Now, let me add some operational flavor to this statement. So if you measure these qubits in the X spaces here, then the outcome would be all 0. So let me define the outcome all 0 as success and any other outcome to be a failure. Then this can be rephrased in such a way that if there is a promise about this state such that if you do this measurement, the failure probability is 0, then this final key is perfectly secret. Okay, this is almost trivial, but I will gradually extend this notion to cover the security of QKD. So this is, of course, this theorem is too weak. So Alice would have an objection, and also Bob would have complaints. But these complaints should be settled by the introduction of entanglement. So what the Alice's complaint is that if she look at her sender and her transmitter, she doesn't find any qubits here. So normally the transmitter, in the transmitter, say the random number is first drawn, and according to this random number, quantum state is generated and sent to above. But you can always replace this by equivalently by introducing entangled state, which is a superposition of this possibility and this possibility using the fictitious qubit here. So Alice can create this entangled state first, then measure this qubit in the Z basis to obtain the bit value. So this and this is completely the same thing. So you can always introduce a qubit like this. Now, what about Bob's complaint? So Bob complains that this is secret also from Bob, so it is useless. So in order to answer to this Bob's question, say we must slightly extend this theorem, tiny theorem, a little bit. So observe that if we rotate these qubits just before this measurement, the basis measurement, then the outcome would be the same. So what I mean is that the final state here and the final state is here if the rotation is along the Z-axis here. So what I mean is that the operations that commute with Z observable for every qubit. So maybe I should say the preserving operations, because this includes not only the rotation, but also some controlled unitary operation from these qubits. So anyway, because the rotation doesn't change this state, we can apply this tiny theorem here, then we obtain this. So showing the failure probability is 0, we are allowed to do any Z-axis rotation before that. So we can freely do this to reduce the failure probability, okay? Now, let us introduce entanglement. So suppose that Alice's qubit here is entangled to Bob's photon in this maximally entangled state. Then if Bob make a measurement to distinguish these two polarizations here, then surely Bob would obtain Alice's final key here. So protocol achieves correctness. Now consider what Bob could have done here. So instead of doing this, Bob could have measured this photon to distinguish these two diagonal polarizations. Then Bob would know this qubit is pointing right or pointing left. So then Bob can give instruction to Alice such that Alice should rotate this qubit and also rotate this qubit, such that all qubits are reset to the value 0. So this means that if we start from the maximum entangled state here, then Bob can do this task completely, perfectly. So this means the secrecy for this key here. So this gives that, say, if you start from a perfect entangled state, actually you would have a perfect secret key. So in the real protocol, Bob tries to guess Alice's final key, but we argue that Bob could have tried to help resetting Alice's qubits to 0 on X basis. And if this can be done perfectly, then this implies that the actual final key here is ideal. It's perfectly secret. Now, maybe you feel that this is just rephrasing that you can create perfect secret key from maximally entangled state. And that's true if you confine this communication here to a classical channel. Then the fact that both tasks are perfectly feasible is equivalent to sharing k bits of entanglement. But this notion here does not have to limit the channel to be classical. So the same argument works if we allow quantum channel here, or if we allow Alice's other systems to be involved here. So the most general statement is that if there is a promise that failure probability is 0 after some doing Z preserving operations here, to resetting Alice's qubit to 0. Then this binary key is secure. So if you are familiar with a state called gamma state or shield, then actually this operation here is a kind of rewinding or unlocking the shield to recover the maximum intact state. So this is the kind of most general description of having a perfect secret key. Okay, so let me make some remark about this. So here, Bob has two choices of tasks, but these two tasks are obviously mutually exclusive, because here Bob learns the identity of Alice's final key, but here Bob actually erases any information about Alice's final key, in not only in the Bob space, but also in the everywhere except Alice. So obviously this task and this task is mutually exclusive tasks. So appearing this pair of tasks which is mutually exclusive is a property of complementarity in quantum mechanics. So in this sense, this phasor approach is connecting the property of secret key to the quantum property of complementarity. Okay, so this is the story about when there is no errors. So next, I would like to introduce the small errors here. So we want a theorem looking like if there is a promise that the failure probability here is not exactly 0, but a small number, then we want to say somehow the final state here is close to the ideal state. So we're talking about how close this state is to ideal state. So what is a proper measure of closeness? Then there is a standard measure used in the QKD, which ensures the universal composable security. So the point is to measure the distance between the two mixed states by using trace distance, which satisfies monotonicity and triangle inequality. And specify this state, if state in the ideal state, to be the same as the real state here. So this equality holds. So always compare the ideal state with this state equal to this one. Okay. And the third one is, this is kind of academic one, but regard system E to be not just an adversarial system, but regard E as everything, every word. And as long as you're proving security against general attacks, then you don't have to worry about this difference, because if you can prove that, then you automatically include everything as a system E. So what I meant about composable security is this. So please recall that actual QKD protocol produces final key and also outputs something like a key length or some public announcement, and also eavesdropper attacks the quantum channel. So there is some quantum interaction here. And let us define ideal QKD protocol here in terms of this actual protocol. So this is actually embedding this actual QKD protocol here, but to just discard the real key here and instead create ideal key, then output this. So difference here is replacing the real final key to ideal key. And let us consider the difference between using actual protocol and ideal protocol. So let us define this state, and this state is the state of everything after carrying out this protocol and this protocol. Now the definition of epsilon security is like this. So the protocol is epsilon secure if it is guaranteed that the trace distance between this state and this state is no greater than epsilon. Then this is a kind of very strong statement. So because due to the monotonicity here, say for any event in the future, a probability of event when actual protocol is used and probability of the same event when ideal protocol was used is almost the same probability, which is bounded by this epsilon. So this event can be something like your company faces bankruptcy, or anything can be applied to this statement. So this is pretty much strong statement. So in particular, in the case of quant QKD protocol, then actual state is related to this state already defined here. And ideal state is related to the state where only the key part is replaced by ideal key. So this is why I insist that ideal state and real state and ideal state should have the same same ideal state of the system. Okay, so actual state was given by some average over the key length k here, and the ideal state is given by this. So the epsilon security in the QKD protocol is look like this. So trace distance is smaller than epsilon. Now, good thing about this measure is that it can be composable. So sometimes we want to measure the imperfection of the case where there are 2 or more protocols are used at the same time. Then you want to compare the ideal situation. But you can always argue that you can make the intermediate situation like this. Then you compare this and this. Then definition of epsilon security assures that the distance between this and this is epsilon prime. Then you compare these two. Then due to the definition of the epsilon security here, distance between this state and this state here is epsilon. Then, thanks to the triangle inequality, you can easily see that the trace distance between this state and this state is bounded by the sum of the imperfection. So, thanks to this, you only have to prove the epsilon security of each of the protocol. Then, the combination of protocols are automatically handled. Okay, so in the ideal case, I separated the whole condition to secrecy for Alice and correctness. And similar thing can be done for this epsilon security. So you can define the epsilon secrecy for Alice, which only concerned about Alice's key. So forget about Bob's key, but use the same similar condition here. And also you can define correctness. So epsilon collect to be the error probability to be no greater than this. So if we define like this, then you can easily prove that if this is true and this is true, then actually the protocol is epsilon secure with epsilon equal to the sum of this imperfection and this imperfection. So this can be easily proved if we consider this kind of intermediate state. Okay, so what we want the theorem looking like, if there is a promise that the failure probability of this protocol is small, then the protocol is epsilon secret. So remaining thing is that the relation between this small number and this small number. But fortunately, this is a very simple relation. So if this is delta, then actually the protocol with the square root of 2 times delta secret. Now the proof of this is a little bit involved. So actually I have written down here, which takes 3 slides. So I'm not going into details here, but I would like to mention why this square root. So square root appears here. Square root appears here. So this is because this failure probability here is written as a fidelity of this input state to the ideal state. Ideal state is all the plus states here. So this quantity is a kind of fidelity of states. So at the end of the day, fidelity of actual state and the ideal state is given in terms of this delta here. But a final statement about epsilon secrecy is given by trace distance. So you must connect fidelity to trace distance. And the only thing we can use is the general inequality here. It is famous inequality, which involves square root here. So this square root appears because we changed the measure from fidelity to trace distance. Okay, anyway, if we consider small imperfection, then say if Bob can help Alice to resetting these qubits to the plus state, if the failure probability is delta, then protocol is the square root of 2 delta secret. Okay. Then next is the practical case. So this scenario, I just think this scenario here would work if entanglement distillation is actually carried out, but normally we don't do that. So what happens in the realistic cases is that even if Bob tried to help Alice, Alice cannot reset these qubits to prostate. So this outcome involves some ones. So I define each of one here to be phase and phase error. So in this case, this protocol almost always fails. So this means that this key bit is insecure. So in this case, this key is not the final key. So this key is called shifted key. And in the actual protocol, of course, we do the privacy amplification to convert in bits to a smaller number of bits. So what we want to prove the security of this final key, what we want is that they say we have some promise on statistical property of the phase errors, so occurrence of ones here. For example, the number of phase errors, number of ones here is bounded by some constant, except a small probability. So if you have that kind of promise, we want to prove that this final key is epsilon secret. But this is our goal. Now here in this talk, I assume that Alice helps Bob by sending some number of bits of encrypted message for Bob to do the error correction. So this consumes many this bits of secret key. So net key gain of the whole entire protocol would be the final key length minus this consumed bits. So I assume this because I want to separate the argument of error correction from the privacy amplification. So this is not mandatory, but in this talk I assume this. So forget about this error correction part. Okay, so what is the privacy amplification here? So privacy amplification here is that actually the multiplication of some binary matrix to the shifted key bits. So privacy implications, the calculation, the computation look like this. And here we are considering the shifted key is the Z-basis outcome of the same number of qubits. Now, at this, I think this point is a good point when I should mention about another approach to the security of QKD, or the other approach. And this is called leftover hashing lemma, started by Renato Rena. So in this approach, actually, we are looking at the correlation between this shifted key to the Eve's quantum system, and somehow quantify the correlation in terms of conditional mean entropy. And if you have a lower bound on this quantity, then there is a leftover hashing lemma, which tells you about the security of the final key. And here, in the phase error correction approach, so we are looking at correlation of these qubits to Bob's quantum system in terms of phase error, statistics of phase errors. So we want to connect the statistical property of this, connect correlation with this to security of the final key. And if you are interested in relation between two approaches, then I refer to this recent paper by Dr. Tsuruma here. Okay, let us continue with the phase error approach. So first thing is rewrite this classical computation to a quantum operation. So we want to do this by using a quantum gates. So this can be done by just extending this matrix to a square full rank matrix. Then multiplication of this matrix can be easily represented by a bunch of control NOT gates. So we can easily create the quantum circuit here. Then we just discard these qubits and only look at the k qubits here and make a measurement on the Z basis. Then we obtain the final outcome here. So this is equivalent to this, okay? Now, what can we say about this quantum circuit? Maybe many of the audience will be familiar about the property of control NOT gate. So a control not gate on some basis, Z basis, for example, is equivalent to another control not gate on the X basis. So if we change the basis, then the control gate actually the target and control is replaced to each other. And this is actually generalized to any matrix here. So control not operation is a operation of this matrix, but on the X basis, this is equivalent to operation of this matrix. But even if when this matrix is larger, dimension is larger, still, if this matrix is C, then this matrix is given by its inverse and transpose. Now using this, if this quantum circuit is written like this in the D basis, then that means that if we switch to the X basis, the same quantum circuit actually compute the multiplication of another binary matrix here. So the pattern of pointing right and pointing left will be transformed into another pattern, which is corresponds to this computation. Now, because these qubits are discarded, why don't we measure these qubits along the X spaces? Then this outcome here is a kind of clue about what the true pattern here is. What I mean is, let's say this bit is the inner product of this row and this true pattern here. So this bit tells you about some clue about this true bit string here. And also recall that we have some promise about this pattern here, like the number of phase errors, number of 1 here is upper bounded by some constant number, something like this. So we have some initial knowledge about this sequence, and we have some clue here. Then combine these two, maybe we can identify this string perfectly. Then actually we know the pattern here of these qubits. So that means we can rotate these left pointing guys such that if we measure these qubits on the X basis, then surely the outcome will be all 0. So if we can do this with failure probability smaller than delta, then this means that the final key after the private simplification is Ipsen secret like this. Okay, so this means that the private simplification to shrinking the n bits to k bits on the Z basis is actually, if we look at the same thing on the X basis, then it's the phasor correction, somehow the same resetting the phasor as to all zeros using the n minus k bits of hints here. Now, what about the amount of private simplification? So what about the length of the final key in terms of this initial promise here? So suppose that number of possible phasor patterns, so possible this string is upper bounded by some number 2 to the constant number. For example, if there is a promise that the number of ones upper bounded like this, then this constant is given by this n times binary entropy of this ratio here. Now, we start from this number of candidates, possible candidates, but every bit here would have the number of candidates here. So repeating this measurement n minus k times, then if this inequality is satisfied, then all the wrong candidates will be eliminated. So this means that if this inequality is true, then roughly speaking, this failure probability would be small. So the key will be secure. So the final key length here is n minus actually this quantity here. This is a rough sketch. And if you want a precise statement, then suppose you can choose a candidate set P of probable phasor patterns such that true patterns here belongs to that set, except the small failure probability here. And the size of the set is bounded like this. And suppose that you choose the final key length k according to this number such that n minus this number and the slightly small So S is a positive integer. Then every wrong candidate in this set would be eliminated by these clues, except probability, this small probability. So this is surely true if this matrix is chosen in a uniformly random way. But actual perhaps application is that it doesn't do that. So that's just pick up from small candidates of matrices. But still, this condition holds if the choice of this matrix is a universal too. So anyway, if this is the case, then actually the possibility of failure here is only two cases. One case is that the true number here does not belong to this candidate set. Then it would fail. That probability is delta 1 here. And another possibility of failure here is that the one wrong candidate survives this elimination process. That probability is that the probability of survival times the number of wrong candidates. Actually, it's this number minus 1. Okay. So the entire failure probability is bounded by this number, but substituting these numbers, we obtain this. So you end up with a formula that final key is 2 delta secret with delta being this number. So this can be made small, and this is also always can be small. So you can make your final key secret as good as you want. So this is summarize the point. So in the actual protocol, privacy amplification is done to shrink to the k-bits, but Bob could have done something to help Alice to reset these qubits to reduce the number of phase errors here. But if there is if you can find this kind of promise here and setting the final key length like this, then you automatically have epsilon secret of the final key with epsilon being this quantity. So this gives the recipe for proving the finite size security against a general attack. So I summarized the recipe here. So first, rewrite your quantum protocol, QKD protocol, such that Alice's shifted key is the z value of qubits here. Okay. Then in actual protocol, Bob do some measurement, but to find what Bob could have done to help reducing the phase errors in this basis. So here, you must be careful that this new measurement here must be compatible to Bob's announcement. So what actually announced by Bob in the actual protocol. So anyway, you only have to find one protocol here. Then if you determine the protocol here, then you compute the bound on the number of phase error patterns appearing here. Sometimes you can just bound the number of ones here is enough to bound the phase error patterns. Then you would obtain finite security here. So this is the recipe in this approach. And I would like to make a few remarks here. So in the asymptotic limit, sometimes people are saying about phase error probability or phase error rate. And the precise meaning of this quantity is like this. So you can bound the number of phase errors to be this value. So some slightly larger than n times phase error rate. And also this inequality is true except small probability. But you know that these two quantities converge to 0 in the limit of large n. So sometimes in the asymptotic limit, you don't know the explicit functional form of these two guys, but you only know that this converges to 0. But that's enough because in that case, asymptotic key rate is given by just this number here. Key rate, efficiency of privacy application here is given by this number here. So finding this phase error rate is enough to achieve the asymptotic key rate. So, and another remark here is that it's a tagging technique called tagging. So sometimes you would find some qubits are higher probability of phase error, and some qubits are lower probability of phase error. In that case, you can argue that each qubit are somehow tagged, and you can classify the qubits according to the tag and assign different phase error probability. So in that case, actually, the number of phase error patterns is given by the product of each patterns, which means that this number is the sum of each tag value. So which end up with the K over N to be 1 minus average of binary entropy of each phasor probability. So this technique is often used in the proof. Okay, so this is the general recipe in the phasor correction approach. Okay. So this is the first half of the protocol. And in the latter half of the protocol, I will give you some examples of quantum QKD protocols. Okay. So the first protocol is the BB84 protocol. So in the case, I consider ideal BB84 protocol using a single photon here. And I assume that this polarization is solely used for the signal, and the diagonal polarization is solely used for the test. Now, as in the prescription, you rewrite this as a entangled state like this. And this is also written like this. So Alice's phase value here corresponds to diagonal polarization here. And Bob, in the signal, for the signal, Bob tries to distinguish these two states, and for the test, Bob tries to distinguish these two states. And I assume that the detection probability has no dependence on the basis for any input. Then we consider this template here. So this is actual protocol. So Bob do this measurement. So we consider what Bob should do in order to reset these qubits to 0 state, plus state here. Of course, the answer is distinguish these diagonal polarization. So good answer is to use the measurement exactly the same as the one used in the test mode. Then phase error in the signal mode happens when Bob has an error in discriminating these two diagonal polarizations, but that error is exactly the same as the error in the test mode. So phase error and error in the test mode is exactly the same thing. So this means that signal mode, phase error in the signal mode and the test mode is just fair sampling. So in the asymptotic, if you're concerned about asymptotic Q length, then you can just apply the observed error rate in the test as a phase error rate here. So this is asymptotic Q length. And if you want finite size security proof, then because this is just a fair sampling, so classical sampling theory is enough to bound the number of phase errors in the signal. So you can probably use simple random sampling, which is more famous. But personally, I recommend to use Bernoulli sampling here, in which each sample is drawn with a fixed probability P. And this is because if you look at the actual protocol, actually signal and test is effectively chosen by a fixed probability. So situation is closer to this Bernoulli sampling. And also in this sampling, you can always have to handle binomial distribution. It's easier than considering hypergeometric distribution. Okay, anyway, in this case, the finite size security proof is also easy to be done. Okay, and okay, so I will skip this. And let me move on to B92 protocol. But before that, I will concentrate on the signal part of the B92, because this signal, binary phase encoding on the coherent states, is common to many other protocols here. So in this encoding, say bit 0 is coded to a coherent state with amplitude plus alpha, and bit value 1 is encoded on minus alpha. And the difference from the BB84 case is that this state 0 and this state pi, these states are not orthogonal to each other, non-orthogonal. So if you write down the entangled state between qubits in the right pulse like this, and if you switch to the X basis here, then actually this coefficient would be different from this. And if this is the coherent state, actually we have here the Schrödinger cat state. So for the plus state, we have even Schrödinger cat states. So photon number is even, and here odd number Schrödinger cat states here. And even though I like 2 photons here, but the main contribution for this state is actually vacuum state when alpha is small. And for this coefficient here, this S alpha coefficient is defined like this. And if alpha is small, it's almost equal to alpha squared, which is the probability of having single photon here. So the probability of having minus state in Alice's qubit is almost equal to probability of emitting single photon here. Okay. So this is a property of signal used in many protocols, including B92 protocol. And in the case of B92 protocol, a measurement is look like this. So B92 measurement, it's 3 outputs, bit 0 and bit 1 and failure. And this measurement is constructed according to expected amplitude. So Alice emits amplitude alpha, but the channel transmission with ether, that means the received amplitude would be beta defined like this. So ideal state received above is plus beta or minus beta. So this measurement tries to distinguish between these 2 states. And this measurement is kind of a null measurement. So this outcome excludes the possibility of input states to be a minus beta state or something like that. And the actual implementation is to shine your photon detector with a local oscillator with amplitude plus beta. In this case, if the input state is minus beta, then interference completely cancels this light. So this detector should not click. So that means that if this detector clicks, then the incoming state is not minus beta. So bit is not 1. So you are sure that the original bit value is 0. So this is the idea in the B92 measurement. Now, you see the template here. So you have entangled state here, and above that's B92 measurement. And let us consider what we should do in this X spaces protocol. So what Bob wants to do is distinguish between even state and odd state here. So one possible choice is to define this measurement as detecting this odd cat state. So if this state is coming in, this bit value is 1. So Bob tells Alice to rotate this qubit. So if you pick this kind of particular protocol here, then you can analyze the phase error probability. So this is not so simple, but here you can choose the orthogonal basis composed of even cat state, odd cat state, and others. Then actually, if Eve chooses other states here, then this has high probability of bit error. So in the optimal attack, this portion would be never used. So important Hilbert space is only 4 dimensions, so spanned by this and this. And due to this correction rule, these 2 pair has no phase error, and these 2 pair has phase error. So you want to bound the amount of phase error here. And you can use the clue obtained in the test phase. So you can use the amount of bit error. Now, the observable of bit error actually depends on the coherence or superposition of this state and this state. So you must consider a qubit state formed by these 2 bases. So this is the kind of bromosphere. Then actually bit error is in this direction. So here another qubit, another bromosphere, and bit error is in this direction. And this green direction here is the probability of finding minus state here. So that probability is in this direction.
Yeah, it seems like we have lost Masato.
Yeah, I think that's lost.
Yeah, I think he'll probably be back soon.
Yeah, I think he's reconnecting.
Yeah.
You're
Okay.
on mute, yeah.
Yeah.
Yep. So can you see that?
Yes.
Okay.
Yes.
Okay. So if bit error is 0, then you only 2 states is possible. And another condition is that the average of having minus state here, probability of having minus state here, must be the same as the initial value, because if cannot touch Alice's qubit here. So this means that average of this and this must be along this on this line here. So this determines the weight of this and this. So this completely determines the bit error probability. Oh, sorry, phase error probability here. So actually, if you compute this one, then you end up with this quantity, which is consistent with beam splitting attack. And if you want to analyze the generalized case with a positive bit error, you must do some numerics. So you must solve the problems of given bit error probability and detection probability, compute the worst phase error probability. Now this sounds like difficult, but this is just a qubit, so 2x2 matrix, so the calculation is not so difficult. And if you want to find outside security, in this case, you cannot use classical sampling theory. You must use something beyond that, and often people use Asimov's inequality here. Okay, so next protocol is a twin field QKD. And okay, so the advantage of this twin field QKD is that the achievable distance is almost doubled, like this. And why it is doubled is because whenever this Charlie detects a photon, then either Alice's photon reaches here or Bob's photon reaches here. So a photon travels only half the distance between Alice and Bob. So this is the reason why this protocol achieves the long distance. Now, today I want to talk about the security proof of this twin field type QKD. And since I'm talking about this binary signal, I want to pick up the variant of this phase twin field type QKD, which is called phase matching protocol. So here, Alice chooses this signal, and Bob also uses this signal and sent to central station. So in this case, actually Bob's part is the symmetric to Alice's part. So what we should do here is actually the copy of Alice's one. So Bob also measures his qubit on the X spaces here. And in order to cancel the phase error here, if Bob tries to send this measurement outcome to Alice. But what is a good strategy of eliminating the phase error as much as possible? So this is done by looking at this property. So here, dominant contribution to the detection is a case where Bob emits single photon, odd number of photons, and Alice emits even number of photons, that is vacuum. So dominant contribution is combination of even, odd, and odd, even. So the good strategy is to reset this reset the this qubit for the case where even, odd, and odd, even. So this is a kind of a strategy to do that. So if you do that, then the combination of even, even, and the combination of odd, odd will result in a phase error here. So in this case, phase error happens when Alice and Bob both send even state or both send odd state. So the estimation of phase error probability is conceptually very easy because you only have to estimate the detection rate when this particular state has been sent to the central station. And actually the rate of this state and this state is also fixed due to this signal property. So only thing you have to do is estimate the detection rate of this single mixed state. So this is conceptually look very simple. But the caveat here is that you can do the estimation by only using lasers, by only using coherent states. So this is where the complication arises, and there are so many proposals to do this in a symptotic regime. And if you want to a finite size solution, then if you like the simple solutions, then somehow there is a technique to reduce this to a classical sampling. You can do that. Or if you're greedy about the key rate, then you can use some improved version of azimuth inequality to obtain finite security of this protocol. Okay. So the next protocol is round robin DPS QKD. So I chose this protocol because I want to emphasize this property. So this approach is based on complementarity, and in some sense, this protocol highlights that kind of property here. So in this round robin protocol, I was going to use block of L pulses like this. And above, make a measurement on the whole block of L pulses using a delayed interferometer here. So this delayed interferometer chooses the value of delay randomly, uniformly randomly between all the combination of delays here. Then Bob has a detection at some timing here. So if Bob detects photon at some timing here, then Bob knows the phase difference between third pulse and fifth pulse. Okay. Then Bob tells Alice the number 3 and 5. Then Alice consults her record of the phase of the third pulse and fifth pulse, then take the sum of them. Then this makes the Alice's shifted key bit. So obviously this bit and this bit should coincide if everything is ideal. And today I would like to make an assumption, which is technologically difficult, but for the sake of argument, I assume that total number of photons in L pulses is no larger than some integer nu. Nu is much smaller than L. And also, instead of this variable delay, I assume that this guy somehow rearranged the order of pulses in a cyclic way. Okay, so under this assumption, the security is proved like this. So here, each shifted qubit is generated from a bunch of L qubits here. So you must first write down this quantum circuit. But this is just, say, hearing the Bob's announcement here. Alice just pick up third qubit and J's fifth qubit here. Then plug in into the control NOT gate. Then measure this qubit. Then this gives the shifted qubit for Alice. So this is what Alice does. And we ask what happens in X basis. So now the assumption that this pulse sequence is very weak. So the promise that the number of photons is no larger than nu means that if you look at this qubit states, no more than nu qubits are in state minus here. So this minus state is rare here. And in order to help to reduce the phase error, Bob switching from this real measurement to this measurement. So instead of doing phase measurement, just Bob does the which path measurement. So if Bob detects photon in this path, so this means that this number 5 is just determined from this random circulation. So nothing to do with input light. So this number 5 is uniformly random over L-1 values, except 3. And because minus state is limited here, and the num J, this index J is chosen uniformly random, the chance of this state being minus state is actually nu over L-1. So this is small. So probability of phase error is small. And what happens if Bob detects photon in this line here? In this case, J is no longer random. So there is a high probability of having minus here. But In this case, Bob tells Alice that Alice must do something. Then what Alice should do is applying the control node operation here. So this is one of the z-axis rotation for this qubit. So this is a route operation. And this quantum circuit can be rewritten using swap gate like this. So this effectively changes the role of I and J. So again, because I state index I is chosen uniformly random, and this control node gate does not propagate the phase error from here to here. So the probability of phase error is also bounded like this. So we conclude that phase error probability is this small number. So asymptotic key length is given by this quantity. And now, important point here is that this phase error is actually constant. This has nothing to do with Eve's attack. So this means that in this protocol, say this part, Eve's attack part, this has nothing to do with quantum mechanics. So Eve has only a small chance to read out the bit just because the signal is weak. So this is contrasted with a conventional QKD in which the focus is on this part. So any measurement leaves a trace. This is quantum property. So normally we think that the quantum mechanics coming in this part. But in this protocol, there is no quantum property here. So only place where quantum mechanics coming in is Bob's part. And that is the property of complementarity I have shown you in the first half of the tutorial talk here. Okay, and the last protocol today, and not least, is a continuous variable QKD. So CVQKD uses homodyne detection or heterodyne detection. And this detection scheme has many advantages, as we heard on the invited talk on Monday. And for example, photo detector is cheaper than the photon detector, or this measurement has a very good mode selecting ability. So this measurement can filter out any different wavelengths or different timing straight lines. So CVQKD seems to be good, but actually this area of QKD was off limit to the phaser approach. However, today I'm happy to announce that at least we can prove the security of CVQKD, one type of CVQKD, by using phase error correction approach. So the protocol is two-state. So kind of one of the discrete modulation protocol, the two-state CVQKD, which uses exactly the same signal state as a B92 protocol. So just plus alpha and minus alpha. The difference is we're going to use homodyne measurement and heterodyne measurement here. So in this particular protocol, for the signal, Bob uses homodyne measurement, and for the test, Bob's going to use heterodyne measurement. Now let us compare this protocol with the B92 protocol. And if you recall the B92 protocol, actually the B92 measurement here has two roles. So one role is on the signal part. So from the signal part, this measurement can select out only favorable events. So this measurement returns 0 or 1 only when, say, this measurement is sure about the outcome. So if the outcome is uncertain, then this measurement returns failure. So this is very helpful to improve the key rate. But for this point, say the heterodyne measurement here can, say, imitate this kind of function up to a certain limit. For example, this is the outcome of the homodyne measurement. And the plus state would be around this, and the minus state is around this. So if you see this outcome here, then you will be pretty much sure the state is plus. And if you obtain this outcome, then you are pretty much sure that bit is 1. But if you have outcome here, then you are not certain about the bit value. So in this case, you can always define it's a failure. So this red curve here is a kind of acceptance probability. So by this way, for the signal part, somehow this CV measurement, homodyne measurement, can mimic the B92 scheme. So having said that, okay, look at this template again. So here, the CV measurement is applied here. So what should we do here? So signal is the same as B92. So what Bob should do is distinguish even number state and odd number state. So in this case, you can directly use parity measurement of the photon number here. This is because as long as this function, I mean, this acceptance function here is an even function, so fixed parity function here, then failure measurement observable or operator commutes with even photon or odd number photon observable. So you can assume that Bob could have done this parity measurement here. So up to this point, it is okay. But in the case of B92, actually, you have to do this kind of, you have to do this kind of phasor analysis of phasor probability. And here you have to use the observed amount of bit error to determine the phase error, right? And this is what is lacked. I mean, what CV measurement lacks. I mean, say in the case of B92 protocol, this measurement in the test mode, this measurement gives the estimation of bit error probability. So this is the second row of this measurement. In the test mode, this gives us the bit error probability. But if you look at this, this probability is equivalent to estimate the fidelity of received state to the ideal state. So the zero state should be arrived at this point as a plus beta state. So this bit error probability measurement by B92 measurement actually tells you about the amount of fidelity here, how close this quantity is close to 1. And problem in the CV measurement is you cannot obtain this fidelity. But somehow we found to do that by using heterodyne detection. So trick is here. So assume this function, which is function mu, which is composed of associated Laguerre polynomial like this. So if you plot this function, this depends on the parameter m and r here. It looks like this function like this. Then we can prove that, say, suppose that omega here is the outcome of heterodyne measurement. So this is some complex number of the outcome of heterodyne measurement. Then input this square of this quantity to this function. Then take an average or take an expectation value when the state row is input to this heterodyne measurement. Then we can prove that this expectation value is always smaller than the fidelity to the vacuum state. And lucky thing is that this is fairly tight. Actually, the equality holds if this state low is weak. If this state low has m or fewer photons, then actually this inequality saturates. And you can, if you can say about vacuum states, and you can just move the position of the origin to beta. You can also measure the fidelity to plus beta state and minus beta state. So this means that you can obtain exactly the same thing as a B92 protocol, which is a bit error probability of fidelity to the ideal state by using heterodyne measurement. Okay, so this means that you can do not exactly the same, but the similar kind of analysis here. You can prove the security of the CV protocol. Now, because this new function here is bounded, so for example, this purple curve is bounded from here to here. Because this is bounded, actually you can prove finite size security using Asma's inequality. And because actually phasor approach is always good against the general attack, so this proof is against general attack. And also because this function is smooth, so you can always incorporate the finite measurement precision. And also this is two-state protocol, it's a finite constellation. Maybe only drawback is that the key rate is not so good. And maybe this is because we are only using two-state. So except for this, actually, as a security proof, this has a very many good properties. So I'm pretty much satisfied as a first attempt from the phasor approach to the CBQKD. Okay, so this is the end of the tour of the various quantum protocols. So I shall stop here and I'm show you the main menu, today's menu again, and I would answer if there is questions. Okay, thank you for listening.
Okay, thank you very much, Masato, for a very nice tutorial talk. Let's go to some questions. And there's already one in the question and answer, but I encourage all the attendees to maybe also ask some questions there or raise your hand in the Zoom if you want to ask a question live. And let me start with the question and answer. I think it's referring to the slide where you showed the relationship between privacy and secrecy. So where you had that if you have delta secrecy, you get a square root 2 delta privacy condition for the other party. And the question is, how can one combine this type of analysis with the finite key decoy state method? So is there also a square root relationship between the failure probability of the decoy state estimation and the secrecy parameter?
Okay, well, I should go back to okay, so decoy state is about, say, BBA for protocol with phase randomized laser pulses. So in that case, you have a tag of photon number. So Alice can have a record of how many photons she has emitted. And of course, and then using this tag, in the asymptotic case, you can divide the rounds to different things. So the question is, say, okay, so how to handle the finite size security here? Okay, so basically it's to make this kind of statement. So using the gathering the data obtained by measuring the decoy state detection frequencies, then you can analyze that, say, how much rounds it's a multi-photon part and how much is a single photon part, and basically you do that in such a way that you can give this kind of statement. So the question is whether square root relationship is applied here, but the square root relation is always here. So only thing you have to do is to solve this problem of decoy state statistics, so which is just a separate problem. So this has nothing to do with this part. So you can always concentrate on rephrasing the decoy state statistics into the form of this type. Then if you do this, if you find this number here, then you can convert to the epsilon secrecy of the protocol. So square root formula is always can be used. So difficult, maybe complication in the analyzing the decoy state finite size. It's somehow you can compare the estimation problem in the decoy state case to formulate in terms of the number of phasor patterns like this.
Okay, thank you for the answer. There's a second question now that is, I think, mostly a question about a reference. You mentioned that you can use any two universal function for privacy amplification. Is there, or where can one find a rigorous proof of this in the complementarity approach? Or is there a rigorous proof of this in the complementarity approach?
Oh, I see. So, okay. So I don't have a reference in this slides, but actually this was done by Dr. Tsurumaru here with Professor Hayashi. So if you, for example, if you look at this paper, then surely this paper has a reference, and you look for the paper by Tsurumaru and Hayashi. Then that paper actually discusses the relation between universality function in Z basis and X basis.
Okay, thank you. And one more question here is it also possible to use these protocols in a two-way quantum communication scenario? So I think with, yeah, it's explained like as a dialogue with forward-backward communication.
Okay, maybe honest answer will be I'm not so sure about that, but my guess is, sorry, my guess is that sorry. This general recipe will work in that case if you can use the property of two-way communication to bound the number of phase errors appearing in here. So even in that two-way communication, eventually Alice makes her shifted key, which is plugged into the privacy amplification. So you can always define qubits corresponding to the shifted key. So the remaining thing is to analyze the phase error occurring in that qubits. So that analysis may be quite complicated if you consider the ping pong type of communication. So actually, conceptually, I think this can be applied, but practically, I don't know if you can obtain a good key rate or not.
Okay, thanks. We have one question here in the chat, which is...
Yeah, actually, I was asking this question. I was just wondering, can you also analyze the 6-state protocol with this approach? So far, you always talked about one or the other basis. Can you also incorporate a third one?
Okay, how should I say? Okay, the 6-state protocol is a kind of tagging. If you agree, say the point crux of the 6-state protocol is that you have two different phase error probability. So one is the case where the Alice's bit value and the Bob's bit value coincide. And the second case is that Alice's bit value and the Bob's bit value, shifted key value, is different. So depending on whether the bit error occurs or not, actually the phase error can be different.
I see.
So in order to analyze 6-state protocol, you somehow make your protocol such that you obtain this tag, which corresponds to there is a bit error or there is no bit error. And the problem is how to extract that information as a tag. And that can be done by, oh, maybe it's so it is difficult to explain only by word, but actually this kind of tag can be obtained by applying, okay, so maybe best one is BB841. this is not, maybe this is not good, but so in the case of 6-state protocol, Bob also has a qubit, right? So Alice has a qubit and Bob also has a qubit. And in order to obtain that tag, actually only you have to do is that apply control not gate from here to here. Then the value of this is actually bit occurrence of bit error. So this becomes tag. And that operation, if you look at on the phase basis, then control not operation from here to here. Mm-hmm. And this is actually the correction operation. So by doing the rotation here, so in this BB84 protocol, I explained that Bob make a measurement here, then instruct Alice by using classical channel, then Alice rotates this. But instead of this, you can do the same correction by applying control not gate from Alice's qubit to Bob's qubit. So that control operation actually do this rotation, and at the same time, the qubit left by Bob, it becomes tag. So if you measure that qubit on a Z basis, then that gives you information about whether a bit error occurred or not. So by doing this, actually, you can analyze the security of 6-state protocol in this framework.
Okay, thank you.
Okay, very good. I don't see any other questions. Oh, wait, there's, I think one just plopped up. Okay, let's do one last question maybe. Is it true to mention that the main advantage of this approach is on DV QKD protocols in comparison with CV QKD? So I think that refers to the complementarity approach, I think. So there is the main advantage on discrete variable QKD instead of continuous variable QKD?
Yeah. So I would say until last year, actually, there is no way to prove the security of CV QKD using this approach. So completely, we gave up completely. But this year, we happen to find one instance where this approach can be applied to the security of CV QKD. But of course, that doesn't mean that this approach can be applied to any protocol of CV QKD. So it will be interesting to say how far this approach can go in the field of CV QKD. But one advantage is once we can establish the security, in this approach, it's easy to do the finite key analysis. That's one advantage. But of course, everything is heuristic, so you can heuristically find this kind of protocol. So compared to the mean entropy approach, say key rate tends to be lower. Mm-hmm. So that might kind of barrier to explore the CVQKD, because CVQKD is a kind of delicate balance between the errors and the gains and loss. So if we have a suboptimal way of doing that, then we might lose everything. That is a concern about applying this approach to the CVQKD. But okay. We'll see.
Okay, thank you very much. And yeah, I think that have been all questions for now. Thanks again for the very nice tutorial. And I think according to schedule, there's now 15, but now maybe 10-minute break, and at 2:30, everyone meets back here for the invited talk.
So, that's correct. And I hope Masato will be available in the meet and greet room for further questions. What people have questions over there.
Yep. Very good. So all further questions delayed to there. And yeah, thanks again for the talk, and enjoy the rest of the conference.
Thank you.
Okay, so welcome back everybody for this afternoon session. I guess it's about time to get going. Just a reminder that if you have any questions, please type them into the Q&A box, and at the end of the talk, we'll go through some of those. And the first talk of this session is an invited talk by Margarida Pereira on QKD with correlated sources. So please go ahead.
Hi, everyone. I'm Margarida. Thank you very much for the introduction. I am a PhD student at the University of Vigo. And first of all, I would like to thank the organizers for inviting me to give this talk at QCrypt. I am very happy to be here. And today I'm going to tell you about QKD with correlated sources, a work that was developed in collaboration with Gokato from NTT Japan, Akihiro Mizutani from Mitsubishi Electric, Marcos Curti, my supervisor, and Kiyoshi Tamaki from the University of Toyama. As you know, there is a gap between the theoretic security promised by the security proofs and the actual security offered by our practical implementations of QKD. One of the biggest problems is the deviation between the idealized device models used in the security proofs and the functioning of real devices employed in our experiments. This deviation might lead to side channels which can be exploited by an attacker to compromise the security of QKD. Therefore, it is crucial to bridge the gap between the theoretic security and implementation security. Perhaps one of the biggest vulnerabilities of a QKD setup to side channel attacks are the detectors. And in fact, several attacks have shown to break the security of QKD by exploiting this deviation between the theory and the practice. Fortunately, this problem is now solved due to the proposal of a measurement device independent QKD, or its variant of twin field QKD. And in these protocols, all the detections take place at the middle node Charles, which is completely untrusted. And this means that the security proofs of these protocols do not make any assumptions on the detectors, and therefore they are not vulnerable to security loopholes on the detector side. Moreover, these protocols have a good performance, so they provide high secret key rates, and they are practical with current technology. So this means that we are pretty much done on the detector side, and the next step to prove the implementation security of QKD is to secure the source. It is typically assumed that the emitted pulses are perfect. However, as you know, the prepared signals always deviate from this perfect scenario due to inevitable device imperfections. And this can lead to side channels on the source. So for instance, we can have state preparation flaws due to the finite precision of modulation devices. So this means that we end up emitting states that deviate slightly from the desired states. It is also typically assumed in QKD that our labs do not leak any information about the internal settings of the transmitters. However, this is not always the case because one can have Trojan horse attacks. So this happens when Eve sends some bright light into the source and then observes the back reflected lights to learn some partial information about LSS settings, or also through spontaneous or passive information leakage to undesired degrees of freedom, such as frequency or polarization. The good news is that if we can model these imperfections and include them into the security proofs, then we can actually guarantee the security of our practical implementations. And in fact, these three imperfections have been quantified experimentally, and recently we have shown that they can be all incorporated together into a security proof. So finally, pulse correlations. It is typically assumed that the emitted pulses in QKD are independent. However, this assumption might not be fulfilled because there might be classical pulse correlations between the emitted pulses. Modeling and incorporating pulse correlations into the security proof is the last step to achieve implementation security. In this talk, I will show you how we can treat pulse correlations. As you will see, it turns out that this imperfection can be incorporated together with all of these. And finally, I will show you how we can prove the security of QKD with correlated sources. Okay, so let me start by first explaining in a bit more detail what pulse correlations are and how do they arise in our practical implementations. So pulse correlations are purely classical and they arise due to limitations of practical modulators, typically due to memory effects. They occur when the state of the emitted pulses depends on the previous encoding. So this means that the setting information is not only encoded into a single pulse, but also into all the subsequent pulses. So for example, ideally, we would prepare these states here where J1, J2, and J3 are the different setting choices for each pulse. However, what we send in reality due to pulse correlations are these states here instead. And as you can see, they have a dependence on the previous setting choice. Classical pulse correlations is a very serious problem, especially in high-speed QKD systems. And in fact, a recent experiment has quantified pulse correlations in both the phase and in the intensity modulator while using a QKD setup with 5 GHz repetition rate. But despite its seriousness, pulse correlations have often been overlooked by the community for two main reasons. First, it is believed that they are very small. However, as we have just seen, at least in high-speed QKD systems, they can no longer be ignored. Moreover, the GLLP analysis has shown that even if an imperfection is small, it can in principle enhance it by exploiting channel loss. Second, it is believed that this imperfection is very hard to model because the state space becomes very large. And in fact, only a few works have considered this imperfection, and none of them deal with pulse correlations in terms of secret key information nor long-range pulse correlations. But fortunately, we have come up with a security framework to deal with arbitrary pulse correlations. And the key idea of our framework is to treat the information encoded in the subsequent pulses as a side channel to our pulse of interest. But let me tell you this in a bit more detail. So let us consider nearest neighbor pulse correlations and the three-state protocol for simplicity. However, our framework also works for arbitrarily long pulse correlations, as I will show you later, and for any number of states. So this is really just for simplicity of discussion. So in this protocol, Alice prepares these states, psi, for one of these encodings, and then she sends them over to Bob in the quantum channel. And typically in QKD, to prove the security of such a protocol, we consider an entanglement-based virtual protocol, which is equivalent to the actual protocol. In this fictitious scenario, Alice prepares her ancilla systems and these pulses in an entangled state, and then she sends the systems B to Bob. So in the case of pulse correlations, this entangled state can be expressed this way, where here A and B are the composite systems of Alice and Bob. These are Alice's ancillous states, and they form a set of 3 orthogonal states in a 3-dimensional space. And these states here are Bob's, are the ones that are sent to Bob, and they represent any kind of nearest neighbor pulse correlations. So for instance, this is the state of the nth pulse when Alice selects the setting Jn given that a previous setting choice was JN-1. So then Bob receives these signals from Alice, and his detectors click for some of them. And later on, they both measure their local systems to obtain the experimental data. And note that the equivalence between this fictitious protocol and the actual protocol holds because these measurements on Alice's ancillas commute with any measurements on Bob's side. So the fact that Alice performs her ancilla measurements after these detections does not affect the statistics of the measurements or the secret key that is generated between Alice and Bob. But importantly, by using this virtual protocol, we can consider what Alice and Bob would have observed if they had measured their local systems in a complementary basis to the key generation basis. And as you learned in just the previous talk, by considering this complementary scenario, we can actually estimate the phase error rate, which quantifies the amount of information leakage to Eve. And to quantify the phase error rate, we typically first obtain the probability of a phase error by considering any attack on a particular detected pulse. Let's call it the kth pulse. And then we ensure security against coherent attacks by using concentration inequalities for correlated events, such as Azuma's or Kato's inequality, or other known techniques. So again, to obtain this probability, we are interested in the state of the kth systems just before the fictitious measurements and that resulted in a click on Bob's side. But in the case of pulse correlations, this is not so straightforward because the setting information of the kth pulse might have leaked to the subsequent pulses. But if we can estimate the phase error rate in this case, so taking into account all these possible leakages of information, then we should be able to guarantee the security of our protocol. So let me explain you this with a bit more maths. So here, to obtain the state of the kth pulse, let's first assume that Alice already measured all of her ancillas before the kth pulse. And again, this is possible because Alice's measurements commute with any operations or measurements on Bob's systems, including these detection measurements. And here we denote with a dash the outcomes of Alice's measurements. And since we are considering the three-stage protocol, this means that now these J's will be either 0Z, 1Z, or 0X. And now let us focus on all the pulses after the kth pulse, so all of these terms here. And note that you can put together this state and all of these terms, and we define a new state, which we call JK plus 1. And then this leftover part comes here directly. And then these two states can be defined as another state, lambda JK. And note that this state depends on all of Alice's ancillas and all of Bob's systems after the kth pulse. So basically, we treat all of the signals after the kth pulse as just a single state, lambda JK. And as you can see, it has this dependence on JK. So then we can write the full entangled state in this form, where again, we have replaced all of these terms after the kth pulse with our newly defined state, lambda JK. And importantly, this is the side channel information about our pulse K. So as I said before, we can treat all the information encoded in these subsequent pulses as a side channel to our pulse of interest. But to understand this formula a bit better, it is useful to compare it with a protocol where there are no pulse correlations. And in this case, our entangled state would be written in this way. And you can see that they are really similar. So the only difference is that here these states that are sent to Bob do not depend on the previous setting, as they do in this case. And also lambda does not depend on JK, as it does here. In other words, this is not a side channel information about this system BK. And as I explained before, in the security proof, we typically estimate the probability of a phase error by considering any attack on this system BK. But in the case of pulse correlations, the setting information about our kth pulse is not only encoded in this system BK, but also into all the subsequent systems. But this suggests that if we can obtain the probability of a phase error by considering an attack on this composite state, then we should be able to guarantee the security. So in summary, we can treat a protocol with pulse correlations as a protocol where Alice prepares these states, where this is the side channel state, and then sends all of these systems to Bob. Okay, so now that you understand a bit more about our framework to deal with pulse correlations, let us consider a particular device model. To understand the intuition behind this model, it is useful to consider the states that we would send in an ideal situation, so in a perfect three-state protocol. And these states can be expressed in the block sphere in this way, where we have 0z, 1z, and 0x. What we expect in the presence of pulse correlations is that these states will now depend on the previous pulse. So they will deviate from their original positions in the block sphere. So they basically can be anywhere inside these cones. And these cones could even be different for each of the setting choices. So then using this intuition, we can express our emitted state in this way, where this is the idealized state that we would send in a perfect protocol, and this part accounts for the deviation from that perfect scenario. More precisely, this is a single photon state that lives in a qubit space. This is a qubit state, and this is a state in the same qubit space that is orthogonal to this one here. And this is a relative phase that, as you can see, depends on the previous pulse. And here, epsilon quantifies the strength of the correlation. And these parameters could be expressed in the block sphere in this way. And as you can see, in this particular device model, in this example, we allow the relative phase to change according to the previous pulse. So this angle theta will vary. However, we fix the amplitudes for all the states. So we fix this epsilon, or in other words, we fix this angle alpha here. Of course, more generally, alpha or epsilon would also depend on the previous pulse. So basically, we could obtain any state inside of this cone. But just for simplicity, we assume this model where we allow just the theta to vary. And of course, our framework could work for other models. So again, this is just a simple example. Also, I would like to remark that when epsilon is 0, so when we have no imperfections, our emitted state becomes our idealized state. So this means that we recover the perfect scenario where we emit perfect states. But as epsilon increases, this term reappears, and then our emitted states will deviate from this perfect scenario. And of course, the higher epsilon is, the stronger the correlations are, and the more information is leaked to a possible eavesdropper. Okay, so recall that we want to prove the security of a protocol where Alice sends these states to Bob. And these states can be expressed in this way, where this is just the definition of lambda JK. And recall that these states here, this one and this one, they represent any kind of nearest neighbor pulse correlations. So again, we just pick this particular example to model these states. So now we can directly plug it in here, and after some algebra, we obtain this final state. Note that this term here is defined as the first term from this multiplication, and all the other three terms, which are actually dependent on the previous pulse, will then come into this state here. And this state is actually a qubit state because this part is independent of JK, and this is a qubit. And this one is a side channel state that is orthogonal to this one here. And importantly, we can now treat our protocol that deals with pulse correlations as a protocol that emits these states here instead of these idealized states. And now we can simplify further this expression by defining the system B as the composite system of all of these, which are all sent to Bob. And note that this includes Alice's and Scylla's because we fictitiously consider an attack on these systems, even though they are not accessible to Eve. We do so to make the maths simpler, but importantly, it doesn't matter how many systems we add as a side channel. What matters is how much our side channel state depends on the setting JK. And this means that this fictitious attack on these systems should not result in lower secret key rates because they do not have any information about JK. So once we make this redefinition, then we finally obtain an equation for the state of the kth pulse. And I would like to remark as an aside that this equation is actually compatible with our previous work, which already treats state preparation flaws, Trojan horse attacks, and spontaneous leakage of information. So this means that we can now put all of these source imperfections together. Okay, so once we have this state, we can then, the next step in the security proof is to estimate the phase error rate. But before I show you how we do it, let me just emphasize that our work also applies to arbitrarily long-range pulse correlations. So more generally, the kth pulse might depend on all the previous setting choices. The good news is that even in this case, even in the case of long-range pulse correlations, we can obtain a state similar to the one we have seen before. So similar to this state. And if you are interested in knowing more about this, I invite you to see me in the meet and greet room, and then I can show you, we can go through all the detailed calculations together for this case. But now let us focus on our objective and continue to prove the security of QKD with nearest neighbor pulse correlations. So when these imperfections are present, this is then the emitted states can then be expressed this way, as we know. And also, we have learned that pulse correlations can be treated as a side channel. So now, to estimate the phase error rate of this protocol and to prove its security, we could simply use any existing security proof that deal with side channels. So we could use the GLLP type security proofs or even the numerical techniques that have been recently proposed. However, these techniques typically require a full characterization of the side channel state, this state here, and some have a poor performance because they are not loss tolerant to state preparation flaws. But fortunately, we have come up with a solution for this too, the reference technique. The reference technique is a framework for security proofs that is very useful to deal with device imperfections, and it can result in high secret key rates. So let me explain you a bit more about the intuition behind this framework. So as with any security proof, our aim is to obtain the phase error rate or the phase error rate as a bound on the mean entropy. To do so, in the reference technique, we first consider some reference states, and these reference states should be similar to the actual states. And then, using the reference states, we can obtain an expression for the phase error rate. And because we have the freedom to pick them as we wish, we can pick them in such a way that this expression is very easy to obtain. And then, because the actual states are similar to the reference states, their expressions for the phase error rate should also be similar. So the idea of the reference technique is to use the reference states as intermediate parameters to estimate the phase error rate associated with the actual states. So now let's see how we can use this framework to prove the security of QKD with correlated sources. So as I said before, it is very nice if we can pick the reference states such that they are similar to our actual states. And also it is useful to select them such that they are in a structured space, such as a qubit space. If we do so, then we can directly use the loss tolerant protocol to obtain an expression for the phase error rate. And this is important because by using the loss tolerant protocol, we can ensure robustness against state preparation flaws. So now recall that this is our states in the presence of pulse correlations. So these are now our actual states. And note again that here we use the 3-state protocol, but this is just an example. So the reference technique can also be used with other protocols. So now, using these two advices, we can select our reference states to be these states here. So as you can see, we select the qubit part of our actual states. And these are indeed very similar. So our reference states are similar to our actual states, since this epsilon should be in principle quite small. And an example of these reference states can be these states here. Note that these states also suffer from state preparation flaws, which we quantify here by this parameter delta. So if delta is 0, then we simply send 0z, 1z, and this state reduces to 0x. However, as delta increases, then we deviate from this ideal scenario. And once we have these reference states, we can then calculate the probability of a phase error. And by directly using the loss tolerant protocol, we find that the probability of a phase error conditional on sending the reference states can be expressed this way, where these are the selection probabilities of Alice and Bob. These are some coefficients that we obtain directly from the loss tolerant protocol, and they can be positive or negative. And these are some conditional probabilities associated with the reference states. So more precisely, this is the probability that Bob obtains the measurement outcome beta, given that Alice selected the setting J. And we call this expression the reference formula, because it will be used as a reference to obtain a similar expression in terms of the actual states. Note that we cannot use this one directly in our security proof because it depends on reference states, which are never used, which are never sent even in reality. But fortunately, by evaluating the deviation between the actual and the reference states, we can bound these probabilities and then obtain an estimation on the phase error rate for the actual protocol. So we call this the deviation evaluation of the reference technique. And this deviation can be quantified using this expression, where here you have some normalized states associated with the actual and the reference states. These are some conditional probabilities associated again with the actual and the reference states, and this corresponds to a lower bound and an upper bound. The mathematical details of this bound are not so important, but it's effectively the bound that was introduced in the low price skills analysis. We could use another bound to evaluate the deviation between the actual and the reference states, such as the trace distance, but this bound is tighter. Of course, if later on we come up with an even better bound, then we can directly substitute it here and our reference technique would still be valid. So now that we have this bound, we can then transform our reference formula into an expression in terms of the actual states. So recall that our reference formula can be expressed this way. And then using the bound, we obtain this inequality. And here, this parameter is the probability of a phase error given that we send the actual states. So this is the parameter that we want to find in our security proof. These are some states that we obtain from employing the entanglement-based virtual protocol, and these are some joint probabilities. So the probability that Alice selects the setting J and Bob obtains the outcome beta. And since we want an upper bound on this one, here we pick an upper bound for the positive terms and a lower bound for the negative terms. And note as well that these two quantities are obtained from experiments, and all of these gray parameters are actually known from the reference technique or otherwise. So once we have this inequality, we can then directly solve for the probability of a phase error. And once we have this quantity, we can find the phase error rate and then calculate the secret key rate using this expression. And you can see that here we are assuming the asymptotic scenario. However, it is straightforward to generalize the reference technique to the finite key regime. And in this equation, this is the joint probability that Alice and Bob select the Z bases, and Bob obtains the detection event. And then, as you know, this is just the phase error rate and the bit error rate. And importantly, to go from this step to this one, all that we needed was an upper bound on the coefficient epsilon. So this is basically all that you need to characterize in your experiment. So no characterization is needed for the side channel states, these states here. And this is very nice because this characterization is supposed to be very hard to do. Of course, if you can somehow do it, then we can add it in our framework, and this would most likely result in higher secret key rates. Also, I would like to remark that existing security proofs that deal with side channels can actually be recovered from the reference technique. So the GLLP type security proofs and the generalized loss tolerant protocol can be regarded as a special case of the reference technique. And then using this framework in the context of pulse correlations, we obtain these results. And here for the simulations, we have fixed delta. So recall that delta is associated with state preparation flaws. And we have fixed it to this value, but of course we could even choose a larger value of state preparation flaws because the reference technique is robust to this imperfection due to the use of the loss tolerant protocol. So our results would be more or less the same, even if this value increased. And now there are two very important points to note in this figure. First, look at the magnitude of epsilon. As epsilon increases, the deviation between the actual states and the reference states increase. So the deviation from the ideal scenario increases, and this causes a decrease in our secret key rate as expected. And also you can see that to obtain reasonable secret key rates, we need very small values of epsilon. So this suggests that further efforts are needed both on the theoretical side to obtain better estimations of the phasor rate, but also on the experimental side to characterize these parameters epsilon. The second point is that our framework works for long-range pulse correlations. So here we have plotted the secret key rate for the case of nearest neighbor pulse correlations, so when I equals to 1, but also for second and for 10th nearest neighbor pulse correlations. And as expected, the more pulses we consider, then the worse the secret key rate gets. But of course, if epsilon is very small, so if we are close to this ideal scenario, then we can ensure the security of QKD for very long pulse correlations.
Okay. You've had 35 minutes.
Thank you. So to conclude, we have introduced a simple formalism to deal with pulse correlations. So basically, we can treat the information encoded in the subsequent pulses as a side channel to our pulse of interest. We have demonstrated that the state the state emitted from a correlated source can be expressed this way. And it turns out that this is in fact compatible with our previous work, where we show that a more general version of this equation already takes care of state preparation flaws, Trojan horse attacks, and spontaneous leakage of information. So this means that we can now put together all source imperfections into the security proof. Moreover, we have proposed a new framework for security proofs, the reference technique, which is very useful to deal with any kind of device imperfections. And finally, as we have seen, MVI QKD type of protocols can remove all the side channel attacks on the detector side. So then if we combine these protocols with what I told you about today, we can actually guarantee the implementation security of QKD. If you are interested about this, I invite you to check out our latest work on arXiv, where we propose a very simple and practical protocol that is secure against any side channel. So basically, this is the only protocol together with device-independent QKD that can claim implementation security of QKD. Okay, so thank you very much for your attention, and I'm happy to answer any questions. Thank you.
Okay, thank you very much, Margarita, for this nice talk. So now we can move to the Q&A. Yeah, please type your questions into the Q&A. We currently have 2 waiting, so we can start with Fred asks roughly how big is epsilon in typical QKD experiment?
Well, that's a very good question, but currently we don't know. So epsilon has not been characterized. So this epsilon, I should say that it can be any kind of imperfection. It can include not only pulse correlations, but also other imperfections. And this epsilon and characterizing how big it is the next big challenge for us. So unfortunately, I don't have an answer to the question.
So you don't have a technique even to estimate or bound epsilon somehow, or like given a model of a device or something? At
the moment, we really need the help of experimentalists, to be honest.
Sure enough.
So of course, you can always put a bound on epsilon. So you can always say, okay, I don't know what are my side channels, but epsilon cannot be bigger than this, right? So you can always do that, but ideally in a security proof, you will go, you will do some kind of characterization to learn exactly like how much this epsilon would be. So yeah, we need all the help we can get and all the interest so that we find this epsilon.
Fair enough.
Great, and there's another question from Ignatius William Primaja. I think your microphone has been unmuted, so would you like to ask it directly?
Yes, thanks for the talk. So I have two questions. I think the second one is pretty much answered. So the first one would be like I suppose in this three-state protocol, you would require some form of like decoy state method. And how would the path correlation affect the decoy state implementation, and how would it affect the overall security analysis?
Okay, thank you for your question. So here in this case and in our paper, we treat, we don't take into account the decoy state method because we are just talking about correlations in the phase modulator. So here we actually, in our model, we assume a single photon source. However, if you consider a coherent source, then we would need to use the decoy state method. But in this case, as you said, we would need to take into account as well the correlations in the intensity modulator. But in principle, this should not be a problem. And in fact, our group is already working on how to extend this to that scenario.
All right, thank you.
Thank you.
Okay, and we have another question from Tim Spiller. I think you've been unmuted. You want to ask directly?
Okay, thank you. I hope you can hear me. I'm just interested to know, given the similarities between a QKD source and one that's used for generating quantum random numbers, whether your techniques can be applied to look at pulse correlations between the successive pulses in a quantum random number generator.
Thank you for your question. I would say maybe, but I don't know for sure. I would need some more time to look into that problem and to then tell you a more concrete answer. At the moment, I cannot say for sure, but I think that our description of the state is very general. So in principle, it could apply to those correlations too. This is just my guess.
Okay, thank you.
Thank you.
Okay, let me just ask one quick question. So you're sort of pushing towards getting independence from the sources and from the detectors. How close is this to being completely device independent, or how would you compare this to something that is completely device independent?
Thank you. So I would say that this is completely device independent. Actually, when you combine it with an MVI type protocol, I would say that this would be completely, yes, device independent, because the MVI type of protocol will take care about will take care of the detector side, and then if we are able to characterize all the possible imperfections on the source, then we can actually ensure implementation security. So the only thing we would need to characterize from the experiment is just this parameter epsilon, and once we do, yes, we can pretty much guarantee practical security the same way device independent does.
Okay, but you need to characterize this epsilon, right? So all of the I mean, there is still some device dependence left, or something in the sense of characterizing this, I guess.
Sure, but I believe that in device independent QKD, you also need to characterize some things. No, I don't know much, so but what I know is that in device independent QKD, you also don't assume that, as far as I know, that you have kind of leakages, right, from
I mean, you have to assume that there's a secure laboratory.
Exactly. So the same way in device independent, you have to do some kind of obtain some parameters from experiment. Here you do too, but in the end, they both can achieve the task of guaranteeing implementation security.
Okay, yeah, I mean, I would say that the assumption about the strong walls of the lab is not really an experimental thing that you obtain. It's more like the same. I mean, I guess you're also making that assumption that you assume that your lab is not leaking.
We do assume. We do assume that we can have leakage of information, no? Because we take into account Trojan horse attacks, for example. So we do assume these kind of leakages.
Okay, but not an arbitrary leakage. Like you cannot have a tiny robot in your lab, for instance.
I mean, we assume passive leakages too from the devices, but having a robot, that one I never thought about. So I'm not sure.
But I mean, is this kind of no leakage assumption that you make in device independent?
No, we do not make an assumption that we don't have no leakages. I would like to emphasize that here we take into account those leakages.
Yes, no, I was saying in normal device independent, it's
okay.
No robot assumption is the analog of the assumption that you're making. It's not really a experimental parameterization. Anyway, let's. Okay, actually, Marcos Curti wants to add something to the discussion on this.
Yeah. Hello, can you hear me?
Yeah.
Yeah, no, it was basically, I think it has been already discussed. So this is an alternative approach to device-independent QKD. So on the one hand, we have device independence as a way to try to achieve implementation security where we don't need to characterize the devices. That is clear. But there is also doubts about its practicality and what kind of rates we can get at certain distances, okay? So of course, there's much work on that and things might improve. But right now, indeed, there is no experiment on device-independent QKD. And also, there are some assumptions on device-independent QKD that have been already mentioned, at least in the current version of security proofs that wouldn't hold in practice. Typically, this is the problem of information leakage that you have already raised. So an alternative solution would be to try to characterize the devices. So, and this kind of solution has been always believed to be very challenging, and maybe indeed it is also challenging. So in this is the path that we have followed in this work, but we have tried to simplify it as much as possible, although there is still the question whether it's easy or not experimentally to really measure or get a lower bound on this epsilon. But we managed to basically put all possible imperfections, including information leakage. So we include all possible device imperfections on the transmitter just through one single parameter epsilon, including pulse correlations, information leakage, state preparation flows, whatever wrong things can go in the transmitter. And then, as Margarita already mentioned, we just save the detector through measurement device independent QKD. So which approach is better? Well, we don't know. So we will see which one is more practical. Right now, both are challenging because this approach also needs to really be able that experiments match this small epsilon. But we are optimistic that probably this could be done eventually. That was what I wanted to say.
Okay, thank you. Yes, I mean, I think it's very nice if you can sort of collapse everything you need to know about the device into a single measurable, in principle, measurable parameter. So yeah, thank you for that comment. Are there any last questions? I don't see any.
Well,
so
I sort of had a
follow-up
question.
Time anyway, so I think we'll end the session there. So. Sorry,
you can ask me later.
Yeah, maybe I'll ask later.
Sorry, a question in the chat. Okay, go ahead, Fred. It seems to be a quick question.
Yeah, it was just a follow-up question to. So I was just wondering how the actual rates compare to the best rates we can get through the IQKD, right? So it seems to be pretty expensive in terms of epsilon, but it's kind of hard to compare to the kind of rates you would get from the actual device independent experiments.
So we haven't yet compared directly these two approaches, but we are actually at this moment working on it. So very soon you will be able to see exactly how it compares. But our prediction is that it will be better than device-independent QKD. Mm-hmm.
Sorry, if I can also add something, because
yes.
actually we know already some of the rates, for instance, for device-independent QKD, depending what kind of technology you assume. For instance, if you assume parameter down conversion sources, of course, if you assume perfect Bell states, the performance will be better. But if we are thinking about something practical with current technology and we just take parameter down conversion sources, then we know that in device-independent QKD, we cannot tolerate much losses.
Right.
So unless one uses a kind of device, qubit amplifier, for instance. And if one assumes even a qubit amplifier, typically the kind of attenuation that one can tolerate is about 10 dBs or 12 dBs, depending on the channel model. And the rates are very, very low. So actually just looking to the figure that is that Margarita has in this slide, we know that the rates of this approach are significantly much higher, several orders of magnitude, and also can reach much longer distances. Okay.
Okay, thanks.
Okay, very good. So we can now, if people would like to continue the discussion, I think Margarita will hopefully go to the meet and greet room, and
yes,
I don't know what floor she'll be on, but you can find in the display there where that will be, and the next session will start then in 10 minutes time.
Oh, Barry, can you see the slides? Oh, okay. Oh, good.
Yeah. Okay, so I think it's time to start the next session then. So welcome back. So in this session, we've got 3 or stroke 4. There's a merged talk, but we've got 3 10-minute talks. So please put your questions in the Q&A as they come up, and mention who your question is addressed to, just to help us when we do the questions at the end. But we won't, we'll wait till the end of all 3 talks before we take the Q&A. Okay, so the first one is by Yanbao Zhang from NTT Basic Research Lab, and he'll be telling us about security proof of practical quantum key distribution with detection efficiency mismatch. So please go ahead.
Thank you for the introduction. So this is a joint work with Patrick, Adam, Jie, and Norbert. So first, let me briefly motivate why we study efficiency mismatch. The first obvious reason is detecting efficiency mismatch always exists in practice. For example, if we would like to measure the polarization state, we need 1 polarizing beam splitter and 2 detectors. Due to fabrication, it is difficult to make these 2 detectors have the same efficiency. Also, the coupling efficiencies of these detectors can depend on their alignment and their setup. This will also cause efficiency mismatch. The second reason is, besides polarization, photons have multiple degrees of freedoms. And for example, so for photons can be in different temporal mode or spatial mode. A detector can respond to a photon differently, depending on the degrees of freedoms of the photon. So if you can manipulate these additional degrees of freedoms, so you can effectively induce efficiency mismatch. People have demonstrated if you can completely control the efficiency mismatch, so you can learn every possible result of Bob. So in that case, perfect intercept and recent attack exist. In this work, we will study the effect of efficiency mismatch on security proof. Before introducing our method, so I would like to first mention there exist security proofs which can handle efficiency mismatch. However, all these proofs assume the system arriving at Bob contains at most one photon, but in practice, so the system received by Bob is an optical signal, which is naturally described by an infinite dimensional system. So this assumption is not justified. And to handle infinite dimensional system, we just introduce a map called squasher. By applying this map, we can treat Bob's system effectively as a finite dimensional system. Inside of this squasher, when the photon number is high, we flag out the Bob's measurement results. So if you can access the squasher, you can learn every possible result of Bob. So for this reason, we would like to ensure the state lives in a small photon subspace with a high probability. So the next step of our method is just try to bound the photon number distribution. We develop method for this purpose. By combining these two steps with a numerical approach for security proof, we can formulate an optimization problem in order to lower bound the secret key rate. In this case, the measurement operators of Bob encode the efficiency mismatch information. So that's why we can study the effect of efficiency mismatch on security proof. So next, I will briefly illustrate our results. So first, we consider the case without mismatch. We would like to study the separate effects of transmission loss and detection loss. The transmission loss is over the public channel from Alice and Bob. Since the public channel is accessible by you, so this loss is not trusted. The detection loss is inside of Bob's lab. Because Bob's lab is secure, so this loss is trusted. Here we just fix the overall efficiency to be 10%. You can see the key rate does depend on how much loss is trusted. So in general, we can distill more secret keys if the trusted loss increases and the untrusted loss decreases. Next, I will study the efficiency mismatch case. So we consider two detectors. There are mismatch between the efficiencies of these two detectors. For security analysis, we can assume Bob's system has at most two photons, or we make a security analysis without such assumption. So we just use flag state squasher. If you compare these two results, you can see by making assumptions on Bob's system, we can overestimate the key rate. We can also consider the mode-dependent efficiency mismatch. By comparing the results with the previous one, you can see mode-dependent mismatch helps you to attack QKD system. The results shown here is for active detection case. Our method can also handle the passive detection case. The details are available in our paper, or you can watch the YouTube video. Thank you very much.
Okay, thank you. So we're going to take all the questions at the end. So we'll now move straight away to the second talk. So, okay, it should be just coming up. So yeah, the second speaker is Ian George from the University of Waterloo, telling us how to do numerical calculations of finite key rate for general QKD protocols. So please go ahead.
So thank you for the introduction. This is joint work with Gia Lin and Norbert Luckenhaus. So let's just get started. So the motivation is pretty straightforward. We now implement QKD in real life, which means we have two problems. One, we have finite resources, which means we need to consider finite size effects. And two, we're going to have imperfections in our devices, which might mess up some symmetries of the given protocol. And so this poses a problem because when we want to achieve tight finite key rates analytically, we normally need certain symmetries in the observations or in the construction of the protocol. And so our solution is a numerical method that doesn't require these symmetries to get tight finite key rates. It uses Renner's framework for finite size effects, which is to say the min entropy framework, and it extends the numerical method for tight asymptotic key rate to the finite regime. So the results of the paper are an improved analysis of the parameter estimation subprotocol for finite size, a general numeric method for the tight finite key rates, and an investigation of these tools for different protocols, but I'm just going to consider one example to show how it works in this quick talk. So the idea of the improved parameter estimation is that when you want to calculate the finite size key rate is you want to construct some set which is going to ignore the states that Alice and Bob will almost always abort on. This is basically the composable security talked about earlier for the parameter estimation subprotocol. The problem with this is that the method for constructing this set traditionally basically suggests that Alice and Bob throwing out information makes them more secure against Eve. The reason for this is because the way you construct this set is by considering the number of joint outcomes of Alice and Bob during parameter estimation. So if you think of BB84, in principle, there are 16 joint outcomes of Alice and Bob, but you could just consider phase error, which has 2. And so if you just consider the phase error, then your key rate could go up because you've shrunk the size of the set S mu. And this is a problem because it's not intuitive. So we showed that this isn't true, that throwing out information can't help you. And the way we show this is by saying, oh, well, it turns out you can take your data and process it in different ways and retain the same security while considering this. So with that idea in mind, we then generate a general numeric method for considering finite size. The basic idea stems from the asymptotic solution, which is you want to calculate this optimization problem of minimizing the conditional von Neumann entropy over some set S, which is the set of states which satisfy some asymptotic observations. And then you start with some guess of the attack rho naught, and then you move towards the optimal attack of the asymptotic problem. And then at some stopping condition, you take that point, you linearize it, and you get the dual and go to the boundary of the set. And this always gives you a lower bound, which is to say that it's reliable. And in the case where rho equals rho star, then this is a horizontal plane. And so you get the true answer. And so it's also tight. And so in the finite key case, you get the same sort of idea. Again, you have this minimization over a conditional von Neumann entropy, but this case, it's over this set S mu that we just talked about. And so again, we can write this as a semi-definite program. And we show that we can do this without introducing any looseness in the problem. And furthermore, we show that we can handle both collective and coherent attacks, which is an important point in the finite size regime. So we'll just quickly consider one example of where this numerical method is useful. So if you think about BB84, Alice is going to send Bob these 4 signal states on the block sphere, but you could imagine that the channel is going to apply a unitary rotation about the y-axis. And so Bob actually gets these 4 states instead, which is to say that in some sense he's received this rotated block sphere, which you could think of as reference frame misalignment. But if they have sufficient parameter estimation, that is to say they have the fine-grained data, they can actually use this in parameter estimation to undo the unitary, which makes the key rate stay the same as if the unitary didn't happen. However, if they did the coarse graining, just considering the phase error that we discussed earlier, then they wouldn't be able to do this. And so this is a problem, at least at the asymptotic limit. So we sort of explore this. So here we see this numerically. If you have these rotated results, the phase error has a better key rate in the small signal limit. But as the number of signals you can use goes up, the fine-grained statistics does better. And this has to do with the fact that you basically can undo this unitary. But then as we discussed earlier, we could consider multiple ways of coarse graining our data. And so numerically, we can consider both. And this gets us a better key rate in all regimes. And this is a major advantage of the numerical method because it's able to handle this optimization problem, which would be difficult analytically. We also note in the case where you accept multiple frequency distributions in your protocol, which is often an overlooked concept in finite key analysis in papers, then this is also a thing that our numerics can do. And this is, again, an advantage because in general, if you have some sort of asymmetric behavior, it's not obvious what the worst frequency distribution in attack would be. And so our numerics allows you to consider this. So that's the gist of it. There's a lot more. So you might want to look at the total talk. But to summarize, we improved the analysis of the parameter estimation subprotocol. We construct a generic numerical method for determining the finite key rate of QKD protocols represented in finite dimension Hilbert spaces, not just this qubit protocol, but qubit MDI, and also optically implemented protocols that can be represented in finite dimensional Hilbert spaces. And then lastly, we consider some examples using this and consider when it might be useful to use our numerical method. We also hope it could be useful for investigating side channels in the finite regime. So thank you.
Okay, thank you very much. And so now we'll move to the merged talk. So the speakers have also, in this case, merged their location, which is very handy. So I think the first part of the talk will be by Ilaria Vagnilusha, if I say that correctly, and then it will be followed by a part by David Bacco. And the talks are firstly overcoming qubit-based QKD with efficient high-dimensional encoding, and then towards high-dimensional quantum key distribution over a 2-kilometer long multi-core fiber. So please go ahead.
Okay, so thank you for introducing. So this works deals with high-dimensional QKD, that is to carry more than 1 bit per photon. And in particular, the main idea of this work is to simplify the experimental setup for high-dimensional QKD. In particular, we address the 4-dimensional protocol with time-bin encoding. So in contraposition with previous works, we didn't use the time of arrival basis, but we decided to test this alternative 4-dimensional basis, where we have only 2 time bins combined in each state. So thanks to this efficient time bin encoding, it is possible to simplify the experimental setup at the receiver. As here we have to project in each basis, we need only 1 interferometer. And these 2 interferometers can be overlapped, as you can see in the figure with the experimental setup at the receiver. So thanks to this efficient time bin encoding, and also by adding an active basic choice at the receiver, it is possible to notably simplify the experimental setup of the QKD system, which requires only 2 single photon detectors. So we have high-dimensional QKD with only 2 single photon detectors, as you can see here at the receiver. And Our results are reported here and in this graph, and are compared with a two-dimensional time-being protocol that we have tested in the same work by employing mostly the same experimental setup. And the enhancement of the secret rate that we have demonstrated here shows that this new scheme that we proposed can be a cost-effective solution for practical high-dimensional QKD with single-mode fibers and time-being encoding.
So the second part of the talk will be to use different degrees of freedom, in particular space encoding, to demonstrate high-dimensional over a special type of fibers that are the multicore fiber. So multicore fibers are well used and well known for the classical communication communities, and actually in Italy at L'Aquila there are deployed multicore fibers of different distances, and they are well used for database, so inter-database communication or intra-city communications. So the idea of this work was to demonstrate that it was possible to achieve let's say a good secret rate generation by using different degrees of freedom. So during the last years, what we have been investigating was we present this concept of using space encoding, but we had a different kind of problems. In particular, we tried to address the problem of phase stabilization. So we can see at this experiment as a sort of a superposition between different cores in a multicore fiber. So up to now, what we have demonstrated was a few meters of distance between the transmitter and the receiver. But with this work, what we did was we combine a phase lock loop in order to keep phase stability together with a QKD setup. So here on the bottom of your left, you can see the QKD, the setup that we used. And in particular, we use two different wavelengths, one for the quantum light and the other one for the stabilization signal. So within the same systems, we are able to propagate the stabilization signal without any modulation by using a smart, let's say, a smart phase loop. And we also send through the same system a modulated QKD scheme at 600 megahertz repetition rate. So here we highlight the two mutually unbiased bases that we used. In particular, you can see that we always use superposition between two cores. And on the plot on your top right, you can see a stability measurement that we achieved actually the last month. So all the spikes, the red spikes that you can see are basically the moment where the phase lock loop lose the stabilization of the systems. But automatically we recover down to a good point. So as you can see, our systems is able to achieve a very, very good quantum bit error rate. The overall quantum bit error rate is 4%, 4.2, for more than 1 hour of measurement. Before conclude, let me thank all the people who has contributed to these two talks that we are presented. In particular, also would like to thank David Ruska and Hugo Spindem for University of Geneva. And thank you for your attention.
Okay, thank you very much. So, well, we've finished all three talks in very good time. So I'm now going to hand over to Li Chen, who's going to organize the Q&A.
Right, thank you. So the talks are open for question and answer. So far, there's been no question typed in, so we'll give a few minutes for people to type in, and please indicate which speaker you have the questions for.
May we ask a question?
Go right ahead.
So for Yan Bao, so actually we were discussing the paper that you presented, and we are asking ourselves, can you use a similar approach to prove a security if you have different dead time of the detectors?
or different data time. Okay. Okay, that's not an efficiency mismatch. That's
I mean, I don't know the answer. That's why, I mean, we are asking also, yeah. Because I think it's, I mean, probably from a technical perspective, it could be that an eavesdropper could use this different that time to for getting information on the key. But maybe it's possible. I don't know.
Yeah, I do not have a clear answer now, but I think it's possible. So our measure is can handle not only efficiency mismatch, but I mean the main idea is we can try to as long as the measurement operator is block diagonal in a photon number basis, then we can apply this kind of squasher, the flag state squasher, to map it to a finite dimensional system. So if the measurement operator still have this block diagonal structure, considering this detector time, data time, different detector data time, so it's possible, but I'm not quite clear how to model this, how to write down the measurement operators considering this data time, different data time. Yeah.
Okay. Yeah, thanks. Yeah, maybe we can investigate it.
Yeah, thanks for your question.
Okay. Now we do have a few questions. One is from Lavi. Go ahead. I enabled you to talk, so go ahead and ask your question.
Yes, thank you. I would like to know for Ian, you mentioned the RFI example, and I was wondering if you could use directly the RFI quantity as in the original RFI QKD paper, like like average of XX squared plus etc., instead of using phase error and full statistics, because that quantity is basically capturing this invariance because of the rotation. So maybe it would be faster to reach the best key rate.
So I guess the one concern from the equation you've put there is that it's taking the squares of expectation values, and normally when you think of the way you do finite size effects, you want to just take the expectation values of each joint outcome. So to answer your question, no, I haven't looked at that, but that's okay. An interesting point.
Okay, I see. Okay, thank you.
Thank you. Next, we have a question from Dev, and the question is directed to Davide. Go ahead, Dev, you can talk and ask the question. Okay, maybe I'll ask. It's for Davide, asking about the refractive index of multi-core fiber. I assume that's the refractive index of the core, or maybe the index difference.
So yeah, you're right in the sense that the standard multi-core fiber, they have more or less the same refractive index as a single mode fiber. So to say something more, the point is one important measurement for quantum communication is the crosstalk between different cores. It means that when you are sending the light into one core, how much light can you get in the other cores? To reduce this effect, it's possible to slightly change the refractive index of some of the cores in order to have less crosstalk between them. So, but it really depends on how big you want your multi-core fiber, so and how many cores do you want, and this kind of things.
Okay, thank you. Yes, I also saw a question from Frederic that is directed towards Ian. Go right ahead, Frederic.
Yeah, so I was wondering, so in your optimization problem, is there a reason why you don't always reach the optimal solution? Like it looks like a convex problem, but it doesn't look like there's anything preventing you from always finding the optimal.
So there's a couple of points. The first one is we're really paranoid about getting a lower bound so that it's reliable. And so when you numerically solve things, you're never going to get the optimal to begin with. The other thing is because of our methodology, we wind up sort of converting from the conditional entropy into a relative entropy, and then we simplify it to something that is nonlinear. So then or not nonlinear, non-convex. So then we do have to do this progression. There's an explanation in the Winnick paper. I could send you a link if you'd like.
Okay, so it's somehow not actually convex in the version you're doing.
Because of our simplifications.
Okay.
Yeah.
Okay, great. And perhaps I could ask a question. This question for Ilaria regarding the time-bin encoding. I know the high dimensional, the purpose is to have higher capacity. But in terms of the time-bin encoding specifically, you still need fairly high-speed modulation for your Z bases. So is there a practical advantage over the qubit case?
Okay, thank you. So regarding this point, that is why we, in the same work, we have tested also a two-dimensional scheme with time-bin encoding. So we have tested a two-dimensional QKD with the same time-bin duration as the four-dimensional. And we created in this condition an enhancement of the secret key rate. So even if there is the same time-bin duration, that means that the two-dimensional state preparation rate is twice faster. We demonstrated an enhancement. So the answer is yes, there is a gain in the overall system.
So is that the curve that you showed was the 2-qubit, with 4D and 2D curve that you showed? I noticed that for the 4D, it has an advantage in the short distance, but then it drops off more quickly. Can you give an intuitive answer to why it is the 4D case drop off more quickly for the larger?
In general, it applies for in every kind of high dimensional encoding, because the fact is that high dimensional is advantageous if you are in the saturation regime of the single photon detector. So at a certain point, when your dark counts become not more negligible, we have that the error rate increases faster if you are in a high dimensional system than if you are in a two-dimensional one. So a random dark count is more damaging if you are in a high dimensional protocol. So the region where you gain in the secret rate is in the saturation regime of single photon detector. Okay.
Okay, thank you very much. That makes sense. Okay, let's see. I don't think we have more questions, so I think we'll end this session, and we will have perhaps more questions and meet and greet in the coffee session. Okay, I'd like to thank all the speakers. Great work. I'll clap in Okay, welcome to another session at QCrypt. So here we have an invited talk by Dr. Yang Liu. The title is Experimental Twin View QKD Through Sanding or Not Sanding. So Dr. Liu, go ahead.
Okay, thank you. This is Yang. I'm from Jinan Institute of Quantum Technology and the University of Science and Technology of China. Thank you for the conference and the organizer for inviting me. My talk is on our recent experiments on twin field quantum key distribution with sending or not sending protocol. Okay, so I would like to introduce the twin field QKD very briefly. Twin field QKD is a new type of quantum key distribution protocol proposed in 2018 by Professor Andrew Schultz's group. This protocol greatly extending the range of secure quantum key distribution with current possible technology. That means we do not need to use quantum repeaters or quantum non-domination detection or other fancy technologies. So it's possible for us to actually perform the experiment recently in this. So there are quite a lot of following up works either on the variant protocols to improve the performance or quite a few experiments till now. I will focus on our experiments, and this is not the full list. There are quite a lot of work in just 2 years. So first, I will talk some QKD performances before the TF-QKD. Here are some list of QKD experiments targeting on long distance key distribution. The by the way, the size of the circle is the secure key rate. So from about more than 10 years ago, maybe 15 years, the transmission distance is increasing in experiment. Till very recently, either with decoy state PPD4 protocol or with MDI QKD, actually about 400 kilometers transmission distance achieved. Is there any limitation to the distance? There might be, actually, especially in practice. Let's use some very practical, very ideal parameter, for example. Let's set the system frequency to 10 gigahertz and use a very perfect detector with 100% efficiency and 0.1 Dacon rate. The transmission distance using single mode fiber is about 500 kilometers, mainly limited by the duck count. Even if we eliminated duck count set to 0, the secure key rate is just 0.1 hertz per second. So it's not that practical to improve the performance further with just this kind of protocol. To achieve longer distance and to improve the system performance. One possibility is to use quantum repeater, and that is the future. We hope to use quantum repeater to extend the distribution distance. And for current technology, we're just using the trusted relay to construct quantum networks, either using fiber to perform the classical to perform the like the 1,000 kilometers fiber network, or using satellite as a classical. But still, the point-to-point quantum key distribution is the key to the fiber network. So improve the performance of point-to-point network is one of the most important things still in the quantum key distribution network. So that is why I think TF-QKD is important. Here, I summarize a few of the key generation rate in quantum key distribution. Sorry. Example, in single photon BPD4 protocol, it's very easy to see that the secure key rate is proportional to the channel loss. And it's similar for other protocols like decoy state BPD4 protocol or MDI QKD protocol. Although the coefficient for each protocol is different, they are all proportional to the channel loss. There are a few theoretical works on this topic. In theory, they already proved that the highest key generation rate in QKD is almost to the channel loss, especially in they call it in TGW and the PLB bound. They are not limited to the protocol I just mentioned before. They are also true for other protocols like CV QKD. In TF QKD, the key rate is proportional to the square root of the channel loss. So this square root proportional is very important because it's possible to achieve even longer distance, like 500 kilometers. In about more than 200 kilometers in practice, it's possible to achieve even higher key rate than the PLB bound like we mentioned. One other note I want to make is the secure key rate of TFQKD is proportional to the single quantum repeater bound. Okay, next I will introduce the TFQKD protocol very briefly. In general, sending and receiving quantum key distribution, we perform the encoding in Alice secure zone and sending the quantum pulses to the channel. In Bob secure zone, we perform the decoding. And next, in MDI QKD, Alice and Bob both perform encoding. In the third-party, untrusted third-party Charlie, or maybe Eve, he performed the detection. So that is possible to enhance the security because all the attacks to the detection is assumed not a problem in theory. For example, in the time-beam phasing encoding in MDI QKD protocol, Alice and Bob are sending signal pulses with reference pulses. The encoding information, the relative phase are encoded between the two pulses. The twin field QKD is very like the above MDI QKD protocol, but the Alice and Bob are just encoding on the signal pulses. There's no relative phase between two pulses. So they are just encoding on the global phase of one pulse. And the difference in detection is Charlie is detected in the one photon interference instead of the two photon interference. We are using sending or not sending TF-QKD. This is a variant of the original QKD performed by Professor Wang. And in this distribution protocol, we have two bases. In this basis, we are sending the signal in small probability, and in the other probability, we are not sending to encode 0 and 1. Actually, the sending is 1. And in X basis, we are sending the 3 different intensities for decoy state encoding. And for all the pulses, the random phases are encoded. In experiment, we are encoded in 16 different phases. So after Chinese detection, we have provided a table to see if it is correct or incorrect. Actually, it's not evaluated. And in X window, we just keep the small amount of the event that the relative phase is within a small phase difference between 0 or pi phases. The phase and the phases in the Z window are never announced, so it's possible to for us to use the decoysed method in theory to analyze the one photon detection and one photon gain. I'm not going to the detail of theory and the security proof, but since we have the decoysed method to estimate one photon component, and we can estimate the Flipping error rate in the X window, so we have the final secure key with fluctuation and the statistic in account. So as a very short conclusion for this part, we have TF-QKD for now. The channel, the key rate is it scales with the square root of the loss, so it's possible to achieve longer distance and higher key rate. And we have SNS TF-QKD as what we are using in our experiment. With this method is because it's not announced the phase information in the basis, it's easier to analyze the security in theory. We can use the decoysed method. And also because we are using a fixed Z probability of sending, the QBER in the basis can be very small. So it allows high basis in X basis. That is, we are allowing the interference to be not that good. Especially it is a one photon interference transmitting to a longer fiber distance. So next, I will talk about our experiment. Why it is not easy to implement this protocol mainly because it's using single photon interference. So that means we need to use two independent lasers with exactly the same wavelength. And that means the laser should be narrow bandwidth and also to be exactly the same. And also we need to compensate the fiber phase fluctuation. Also in the SNS protocol, it requires the duck count rate of the detector to be very, very small. So next is our experimental setup. Here, we are using two independent laser sources. The laser source we are using is narrowband laser locking internally to ultra-stable cavity. I'll introduce it later. The two laser sources locking through a separate fiber link. And we set the fiber link, the length of the fiber link to be at least the same with the signal fiber. The signal, the current light is split in signal channel, and in this channel, we have a phase modulator to modulate the different phases, and we have 3 amplitude modulator to generate the signal pulses as well as the phase reference pulse. Entirely, we interfere the two signals from Einstein bulb and beam splitter and detect the signal using superconducting single photon detector. Okay, so the phase stabilization is the key to this experiment. The phase interference may be not that good because of phase fluctuation, and this may come from the wavelength difference or the fiber length fluctuation. To make sure that everything will be good, the first thing is to make sure the laser is good. What does it mean? It means the laser is a narrow bandwidth laser, and also that is not enough. We need the central wavelength to be very stable. For example, if using a narrow bandwidth laser in lab, the central wavelength, if it is fluctuating, still the interference result is fluctuating. Here we use a 20 kilometers unbalanced interferometer for testing. So that will test the central wavelength fluctuating. And the testing result for our cavity locking laser is the best in either the interference result, or we can see the spectrum of the noise. It's also the best. The length of this laser is about 1 Hz. It's very good. And the next thing we need to do is to lock in the wavelengths in Alice and Bob to be exactly the same. But we are doing this by splitting the laser into two. One is internally locked the actual stable cavity using PDH technology. And the other part is sending from Alice to Bob. Bob lock his laser wavelengths to Alice with using a detector. And his locking result is split into part of this result is going to the QKD system. And to eliminate the phase fluctuation in the path, we send the laser back from Bob to Alice. And Alice is also locking the phase difference using a photon detector to see the beating. We are using 9 ADFAs in this 500 kilometer fiber that control the signal intensity below the threshold for stimulated Brownian scattering. So we tested the locking result. First, we testing using a single source with 150 kilometers fiber. The fiber drifting, the phase drifting rate is about 7.1 radius per millisecond. And next, we're testing using 2 independent lasers locking to each other through 500 kilometers fiber. The drifting rate is about 9.6 radius per millisecond. So by this 500 kilometers, we mean that both the source are separated by 500 kilometers with the this locking fiber and also the signal fiber. So actually, we attributed the phase drifting mostly coming from the fiber itself. The next thing we need to do is to compensate the fiber phase drift because of the thermal noise or the sound noise. So we are designing a signal pattern with sending between signal. We are sending some reference light, very strong reference light for phase estimation. In every 5 microseconds, we're sending in 3 microseconds for signal and the other 2 microseconds for the reference, phase reference. Sending in at least for 4 different reference, and actually the phase difference are the 4 phases. So we can model the result, and we can estimate and optimize the relative phase between Alice and Bob to get it to calculate it. So there are a few requirements for our design because we want to estimate the phase difference of the signal. We need to set the wavelength of the reference light and the signal to be exactly the same. And also they need to travel to through the same of the fiber path. So also we need the intensity of the reference light to be relatively strong. In our experiment, we set it to about 2 megabits per second for quick estimation. We can do this estimation in 10 microseconds. So that requirements, that's a strong requirement for detector because we need the about 2 megahertz detection rate. That's the positive detection rate, as well as very low dark count rate for signal, actually in very short recovery time. So we're using simple conducting nanowire detector with some improvement. The we use parallel configuration in 9 different parallel detector units to reduce the connected inductance and to reduce the recovery time. We're using 50 ohm shunting resistor to prevent the detector from latching. So in testing, we have 10 megahertz detection rate with continuous LED input. And that means it's possible for us to use 3 megahertz as a post test. And we are for the duck count, we are using the detector integrated inside the detector, a narrowband filter to reduce the duck count from the thermal noise and also to reduce the insertion loss. A smaller active error of 16 micrometer is also a possible method to reduce the duck count from the detector itself. So we achieve about 60% of the detection efficiency with about 3.5 Hertz duck count rate. Next, I will show our experimental results. There are some parameters in common. We're using just a normal fiber spools in transmitting the signal. We did not do stabilization, so we think it is possible. This fiber spools are most practical. We can put it into field test without some more modification. And also, we are setting the failure probability of the protocol to 10 to the minus 10, considering the finite size effect and the statistical validation. In our first experiment trial, we achieve about 150 kilometers transmission distance. We're using a detector with rather high duck count rate and relative high system efficiency. We did not do the phase modulation optimization, so the Q-bar in X species is rather high, actually. It's more than 10%. But at the same time, we proved it's possible to generate secure keys and transmission through long distance with this protocol, even if the X species Q-bar is high. And besides, we are using some gating method in our experiment. We set some gate in timing for the pulse. We only keep the central part of our pulse, so the time difference in the rising or falling edge will not affect the phase interference. And also, we are setting the gate for phase estimation. We only keep the part of the signal that we are confident the phase estimation is good. Next, we improve the phase modulation, and we also using a bit better photon detectors with about 100 Hertz duck count rate. So here we achieve about 300 kilometers distribution distance, and the secure key rate is actually higher than relative PLB bound above about 240 kilometers. Here you can see that the phase error can be controlled to be very small, actually, in experiment through 300 kilometers. And in this experiment, the phase modulation and phase interference is good. So we do not use any gating in the phase estimation. We keep almost all data because of the phase estimation. The Q-bar in ZBase is a bit high. This is an optimized result from theory. Although we are sending the pulses in ZBase basis a bit higher, so the Q-bar might be higher, but actually we have more key rate because the pulses are higher. So next, we perform the final experiment with ultra low duck count rate, about 3.5 Hertz, and about 60% of the detection efficiency. With this parameter, we achieve 500 kilometers distribution distance using ultra-low loss fiber. And in 400 kilometers, the key rate is orders higher than Freiberg's experiment, the decoy state and MDI-QKD experiments. In performing this experiment, we found there are a few other sources of the noise. So besides the dark kernel itself, there's a noise from the relay scattering. Generally, when we think about relay scattering, if the direction of the relay scattering is the same with the laser, it will not affect the signal from the reference because we are sending the reference pulses, very strong reference pulse, as well as small signals. The relay scattering in the same direction will not affect the signal because the wavelengths are the same, there's no dispersion. And the scattering in the backward direction will not affect because it's different direction. But actually the backward scattering will generate another backward scattering. So that will be the same direction with the signal. Although the relay scattering is not strong, the relay scattering, this is what we call this two backward scattering, can distribute uniformly in time domain with the signal. So we cannot distinguish this noise from our signal, either in timing or in wavelength filtering. We model this effect and estimate the noise of the relay scattering to be about 10 count per second for our experiment. This is already much more than the noise from the detector itself. But it's still good for experiment in 500 kilometers. It might be problem in even further experiments in the future. So we are introducing the two-way communication in the post-processing in our experiment. For two-way communication, we can consider we are getting some result from the 16 bits, and then we group 2 bits together to perform a parity checking. In doing this, we can eliminate the always wrong bits and decrease the Q-bar in Z basis. For the Q-bar in X basis, we can estimate the using standard two-way classical communication method. Actually introduced this thing in 2002. To the phase error in X basis may rising, but because the Q-bar in Z basis decreased dramatically, we have gain. And there is observation that the Q-bar is not uniformly distributed in the odd or the even parity. So if we just keep the odd parity 16 bits, we can further decrease the Q-bar in Z basis. And if we can actually preparing the bits in odd parity, we can actually further enhance the system performance. So here, you can see that the original Q-bar is about 10%, and after this two-way communication, it decreases to about 1%. Although in the X basis, the phase error increases about double its phase error rate from 6 to 13. But actually, because the Z basis is a big decrease, so the distribution distance can be longer and our Q rate is actually higher. In this 500 kilometers, in using the standard two-way communication, we already have higher key rates than absolute PLV bound. If we are using out pairing or LPV pairing method, we can achieve even higher key rate. So that is what we have for our experiment for now. And next, in the future, we hope to put the TF-QKD in field testing because the parameters we're using in our experiment is, I think it's rather actual in practice. So there should not be much difficulty in putting it to field test. And we hope to improve the system in the future. And I hope to see other experiment either performing in free space or using other variant of the original TF-QKD protocols. This experiment is done in University of Science and Technology of China in Professor Qiang Zhang and Professor Jeremy Pan's group. And I would like to thank our collaborators working on theory in Tsinghua University, and they're working on the high performance single photon detectors in Shanghai Institute of Microsystem and Information Technology, and the company providing us the ultra low loss fiber from Corning instrument. And also, I would like to thank the acknowledge the funding agencies for our experiments, and I would like to thank you for your attention. Thank you.
Thank you. So I'm going to clap for all the audience. Thank you, Dr. Liu, and we are open for questioning. So again, remind everyone, please type in your question in the Q&A section. And I see here that Bruno has raised his hand. That's actually quite early on in the talk. Is there a question from Bruno? Okay, let's see if I can, no. No, okay, I don't get a response.
Okay.
Hold on. No, okay, I don't know. He's allowed to. Okay. Oh, there is a question from Dev. I'm going to allow him to talk here. And his question is, what's the largest distance on which qubit is transmitted so far?
Okay. I think we have 500 kilometers transmission of the quantum key distribution. And I remember there's another work. It's also transmitting qubit about 500 kilometers. I think this is the longest distance in fiber for now for quantum key distribution. And also in Jeremy Pan's group, we are performing the key distribution and also teleportation and other things with satellite. So it's possible to transmit with about more than 1,000 kilometers using satellite and free space.
Very good. Any follow-up questions for that? Okay, I have a couple of questions. Again, the work is very, very impressive with locking the laser to 1 hertz with the kind of distance that you have demonstrated. It's basically really the state of the art in the devices in the detectors and in QKD itself. So my question here is have you tried to do the asymmetric? How sensitive is this experiment when you have the distance Alice to Bob and Bob to, Alice to Charlie and Bob to Charlie distance? There's an asymmetry. I know your laser line width is very narrow, so that should give you an advantage in doing the asymmetry. Can you comment on that?
Yeah, thank you. And as for asymmetry, I think it's much a theoretical problem because the theory will tell us how long we can distribute if using asymmetry setup. And we discussed with professors working on theory, and our result is we can have some kind of asymmetry, like for example, 100 kilometers asymmetry, the performance will not decrease very much. But if the asymmetry is too much, for example, if for one side is 400 kilometers, for other side is 0, maybe, I'm not quite sure if we can get a final key. There are some limitation for this, for the protocol we are using for now. We we hope to put it into test in the future, because this is also one thing that is important in field testing in practical scenarios.
Right, exactly. Do you foresee any experimental difficulty in implementing an asymmetry experiment?
I think there's not much difficulty in putting into experiment. We need theoretical support, actually. Yeah.
Thank you. We have a question from Roloff. I'm going to enable the voice. Roloff, please go ahead.
Thank you very much, first of all, for your talk. And I was wondering, what kind of optical fibers did you use when you found a noise of 8.6 on the 500 kilometer distance?
Okay, thank you for a question. We're using ultra-low loss fiber from Corning. Actually, in our experiment, in our testing, we found the noise, re-release scattering noise, is much related to the channel loss, actually. So if I'm using standard fiber with similar the similar loss, the noise should be similar. It's not much different.
Okay, great. Thank you very much.
Thank you.
Thank you. Next, we have a question from Harold. Harold, go ahead. I have enabled your voice.
Hi, great experiment, but wouldn't it be easier to just use one laser in the middle, so at Charlie's position, distributing the light instead of this cumbersome synchronization?
Yes, thank you. Yes, it's much easier to use just one laser to distribute light to Edison bulb and getting back. But we have some security concerns, because if Edison bulb are not using independent lasers, we have the security concerns if there can be some toy house attack to the system, if there is a channel input into the encoding system. It's much harder to guarantee the security. So we decided to use two independent lasers. Although it's very hard in experiment, the security should be higher.
Okay, thank you. Just a follow-up. Yes, you are using the two independent lasers, but you still have a locking mechanism. So there's still a laser signal coming out of Alice, going to Bob, and coming back for locking. So wouldn't it the same attack that can be launched there? Is there an argument for, potentially you're still opening up this possibility?
Yes, thank you for the question. I think the scenario is a bit different, because in our locking system, we actually it's not the same as because the laser is not coming from Charlie to Alice system and going back to Charlie. The path is different. In our locking experiment, in Alice and Bob's laser is. The laser itself is just sending out pulses, and the locking is a kind of baiting. So it's a baiting from the continuous laser in Alice, and the light from Bob, it's a baiting to a detector. So in general, a Troy house attack if we want to perform that kind of attack, the signal should be coming to the system and going back. But for our system, the input channel will never going out to the system. And also, I think this locking is used as a reference. In our experiment, actually, we can keep the system locking for example, for a few minutes, and then we keep the channel, the locking channel breakout for 1 hour. The system can be running because our system, our cavity locking system is very stable.
Okay, okay, thank you. Next, we have a question from Marcos. Marcos, I have enabled your voice. Go ahead.
Hello. Well, first of all, I'd like to congratulate for the talk and for the amazing work. So it's really fantastic. And I just have a curiosity because there are some skepticism in the field whether or not MDI-QKD or twin field could be at some point or eventually relevant for free space communications, or they are too challenging. So from your experience, I just wanted to know what is your opinion.
I hope I get your question. I think it's possible for free space communication because I know that in Pan's group we have already performing at least trying to perform the MDI-QKD experiment. I don't know if they already have the result, but yes, I think we have some good results in performing MDI-QKD. And it's even more challenging in doing TF-QKD, but still, I think it's possible. I'm not quite sure if this is the best choice for free space communication using the satellite, because it's moving the channel distance between Alice, Bob, and Charlie are always changing. So it's even harder to compensate the path difference. But at least for now, I think it's worth to try.
Okay, thank you.
Thank you.
Thank you. Next, we have a question from Dev again. Please go ahead. I have enabled your voice. Hello? Okay, then I will ask the questions. I'll read it off the Q&A. It says, how can we maintain the coherence in qubit during such a long journey of qubit transmission? I mean, noise fluctuations during path.
Okay, thank you, Dave. Thank you for the question. It's actually a very good question. Let me see if I can have some slide here. Yeah, the coherence of the qubit coming from a few different paths. The first important thing is the laser itself. Because we're using very narrow bandwidth laser, the coherent length of the laser of the qubit is very long. So we can tolerate the length difference for this is the first thing. And the next thing is we're locking the two lasers, as you know. So actually, when the qubits getting together in Charlie, it is coherence. It is coherent. And the next thing about the fluctuation, we are using the reference light. We can read out. Actually, we can estimate the phase difference between Alice's fiber and Bob's fiber at Charlie. We can do it very fast. Yes, there are some. There are the phase fluctuation in the past, like for example, you can see that it's about 10 radius per millisecond. It's drifting very much, but generally you can think about in about 10 milliseconds, it is stable. So it's possible for us to compensate the phase difference.
Yeah, okay, very good, thank you. And finally, we have a comment from Chang in response to Marco's question. He pointed out to your archive paper that's typed in the Q&A session. And that is MDI-QKD experiment in free space. I think everyone can see the questions. Chang, I'm going to enable your voice if you want to add some comments to that.
No comments, thanks.
Okay, all right. So I think everyone can see the Q&A, so they will see your link.
Yeah.
Okay, let's see. We have no further questions. So thank you very much, Dr. Liu. Great work. And that brings us to the end of the technical session today. There will be an end of day meet and greet at the REMO tables. So I will stop